Hello there, and welcome to Life Beyond Seen, where curiosity gets comfortable, questions slow down, and science is allowed to wander at an unhurried pace. This is a place for long thoughts, quiet explanations, and ideas that don't demand your full attention all at once. You can listen closely, or you can let the words drift by like background noise while the day finally loosens its grip. Either way is perfectly fine. Tonight we're heading somewhere very few humans have ever been, and even fewer could remain for long. Not because it's forbidden, or protected, or marked with warning signs, but because the place itself quietly refuses us. Far below the waves, past sunlight, past familiar pressure, past anything that feels remotely human, lies the deepest part of the ocean. And while we can visit it briefly, in carefully built machines, we cannot stay there. Not comfortably, not safely, not in any ordinary sense of the word. Before we sink into that depth together, let me ask you something gently, the way one does when there's no rush for an answer. Where are you listening from right now? Are you somewhere bright or somewhere dim? Is it early in the day, or has the world already gone quiet around you? It's a curious thing to think about, really. While we're talking about a place nearly 11 kilometers beneath the surface of the Pacific Ocean, you're here, wherever here happens to be for you, anchored by gravity, air, and a pressure your body understands so well that it never even notices it. And if you find this kind of slow exploration calming, or interesting, or simply a good companion for a tired evening, you're always welcome to let me know with a like, or by subscribing. It helps this quiet corner reach others who might appreciate a gentler way of learning too. No urgency, no pressure, just an open invitation. Now, imagine standing on a shoreline. It doesn't matter which one. Any coast will do. Waves roll in, waves roll out, and the ocean looks familiar enough. Blue, restless, reflective. You might think of it as vast but still approachable. Boats cross it. People swim in it. Planes fly over it. From the surface, it feels like something we've mostly figured out. But that impression fades quickly once you start going down instead of across. The Mariana Trench begins like many other deep-sea features, quietly. There's no sign on the surface telling you that you're floating above the deepest known point on Earth. No change in wave pattern, no darker shade of blue, just open water, stretching in every direction, giving no hint of how far it continues beneath you. Yet below that calm surface is a descent so extreme that if you dropped Mount Everest into it, the peak would still sit more than a kilometre underwater. At the very bottom of that trench is a place called the Challenger Deep. It is deeper than any other known point in the ocean, reaching pressures so immense that they're difficult to describe without slipping into numbers that stop feeling meaningful. But we'll take our time with that. For now, it's enough to know that the environment there is not just hostile in the dramatic sense, but fundamentally incompatible with the way the human body works. Humans are, in many ways, surface creatures. Even those of us who love the sea are adapted to a narrow band of conditions. We breathe a specific mix of gases. Our cells rely on precise pressures to function correctly. Our bones, blood vessels and organs evolved under the steady, forgiving weight of one atmosphere pressing down on us from above. That pressure is so constant, so familiar that we never feel it. We only notice pressure when it changes. If you've ever felt your ears pop on a plane, you've already experienced a very mild version of what pressure differences can do. That sensation comes from a relatively small change in atmospheric pressure over a short period of time. Your body adjusts quickly, and the discomfort passes. Now imagine that sensation continuing, intensifying, multiplying, not by a factor of 2 or 3, but by hundreds. At the depth of the Mariana Trench, the pressure is more than 1,000 times greater than the pressure at sea level. Every square inch of surface area is being pressed by the equivalent weight of dozens of large commercial airplanes stacked on top of it. This pressure is not aggressive or sudden. It doesn't rush at you. It simply exists, constant and inescapable, pushing inward from every direction at once. Water is heavy, and the deeper you go, the more of it sits above you. Each additional meter adds a little more weight. Near the surface, that increase is manageable. Divers adjust, equalize, move carefully. But there is a limit to how much adjustment the human body can perform before the systems that keep it functioning begin to fail. One of the first problems is air itself. Our lungs are designed to operate within a narrow pressure range. As external pressure increases, the air spaces inside the lungs compress. Breathing becomes more difficult, then dangerous. Gases behave differently under extreme pressure, dissolving into the bloodstream in ways they normally wouldn't. Nitrogen, which makes up most of the air we breathe, can become toxic at high pressures, interfering with nerve function and cognition. Oxygen, essential at the surface, can also become harmful when its partial pressure rises too high. This is why even experienced deep-sea divers cannot simply keep going down indefinitely. Specialized gas mixtures, slow descents, and strict time limits are required to prevent serious injury or death. And even with all of that, human diving records stop at depths that are still tiny fractions of the Mariana Trench. Beyond breathing, there is the issue of structural integrity. The human body is remarkably resilient in some ways, but it is not built to be compressed evenly from all sides by enormous force. Blood vessels, organs, and tissues depend on pressure differences to move fluids and exchange gases. When those differences are overwhelmed, systems that normally operate automatically begin to struggle. The heart, for example, relies on pressure gradients to circulate blood effectively. Under extreme external pressure, maintaining those gradients becomes increasingly difficult. The kidneys, responsible for filtering waste, are sensitive to changes in blood flow and pressure. The nervous system, which transmits signals through delicate electrochemical processes, does not respond well to environments where the physical behavior of molecules starts to shift. Temperature adds another layer of challenge. The deep ocean is cold, not in the way a winter day is cold, but in a persistent, draining way. Near the bottom of the trench, temperatures hover just above freezing. Without protection, the human body loses heat rapidly in water, far faster than it does in air. Hypothermia becomes a serious risk long before pressure reaches lethal levels. Then there is the darkness. Sunlight does not penetrate anywhere near the depths we're talking about. Long before reaching the trench, light fades to black. Not dim, not twilight, but complete absence. Vision becomes irrelevant. Time perception changes. Orientation becomes difficult. Even with artificial lighting, the sense of isolation is profound. This combination of pressure, cold, darkness, and physiological strain creates an environment where survival depends entirely on technology. Humans can visit the Mariana Trench only inside vessels designed to withstand forces that would otherwise crush us instantly. These submersibles act as artificial pockets of surface conditions, maintaining pressure, temperature, and breathable air while the ocean presses relentlessly against their outer shells. But even inside these machines, time is limited. Systems must function perfectly. Power must be conserved. Any failure becomes immediately serious. There is no rescue waiting nearby. Communication with the surface is slow and fragile. The deeper you go, the more final every decision feels, even if the mission itself is carefully planned. It's worth pausing here to consider how unusual this is. Humans have adapted to deserts, mountains, polar ice, and even low Earth orbit. We can stay in space for months at a time. We can build habitats in environments that seem, at first glance, completely uninhabitable, and yet the deepest part of our own planet remains somewhere we can only briefly touch, like a fingertip against something too hot or too heavy to hold. This isn't because we haven't tried. Over the decades, engineers and scientists have designed stronger materials, better pressure vessels, more reliable life support systems. Each advancement allows us to go a little deeper, stay a little longer. But the fundamental mismatch remains. The human body does not belong there, and it never evolved with that environment in mind. As we continue downward in this story, it becomes clearer that the Mariana Trench isn't dangerous in a dramatic, cinematic way. There are no lurking monsters waiting to attack, no sudden explosions of violence. Instead, it is dangerous in a quiet, indifferent way. It simply exists under conditions that do not care whether we are present or not. And that indifference is part of what makes it so fascinating. Because while humans struggle to survive there even for hours, life itself has found ways to exist under those same crushing pressures. Creatures with soft bodies, slow metabolisms, and biochemistry, adapted to extremes, move through that darkness without effort, as if the weight of the ocean were nothing more than background noise. Understanding why we can't stay there for long means understanding not just the trench, but ourselves, our limits, our design, the invisible assumptions our bodies make every second we're alive on the surface. As we sink further into this explanation, those assumptions start to come apart one by one, revealing just how narrow the slice of the universe we're built to inhabit really is. And with that in mind, let's continue downward, slowly, into the growing weight of water, and look more closely at what that pressure actually does, not in theory, but in practice, to anything that tries to resist it. Standing at the surface of the ocean, it's almost impossible to grasp how far down the world continues. Even if you know the numbers, even if you've seen diagrams or animations, the distance refuses to feel real. Water has a way of hiding depth. It reflects the sky, moves with the wind, and gives no obvious indication that beneath it lies a vertical journey longer than the height of the tallest mountains on Earth. From above, the ocean looks like a wide, flat expanse. From within it, depth reveals itself slowly, layer by layer, as conditions change in ways the human body immediately begins to notice. The descent toward the Mariana Trench does not begin dramatically. At first, the water behaves as expected. Sunlight penetrates easily. Waves fade into gentle motion. The pressure increase is subtle enough that most swimmers would never think about it. This upper region of the ocean, known as the epipelagic zone, extends down to about 200 meters. It's where nearly all familiar marine life exists, where coral reefs thrive, and where human activity comfortably reaches. Scuba divers operate here with training and equipment. Boats drop anchors, and underwater photography captures scenes that feel vibrant and alive. But even within this relatively shallow zone, the distance downward already exceeds what most humans ever experience. 200 meters is taller than a skyscraper, and that's just the beginning. Below this, sunlight weakens, colours fade, reds disappear first, then oranges, then yellows. Blue lingers the longest, which is why the ocean appears blue from above. As light diminishes, the environment begins to feel less like a place and more like a gradient into something unfamiliar. At around 1,000 meters, sunlight is effectively gone. This is not darkness in the way a room becomes dark when a light is switched off. It's a complete absence of natural illumination, a condition where no biological rhythm based on day and night can exist. Here, vision becomes less useful, and many organisms rely on other senses to navigate their surroundings. Pressure has increased significantly by this point, roughly 100 times greater than at the surface. For humans, this depth is already far beyond safe diving limits. Without a rigid, pressurized vessel, survival here would be measured in moments, not minutes. Yet this depth still represents only a fraction of the journey to the Mariana Trench. As the descent continues, the scale becomes harder to keep track of. Depth markers lose meaning. The surface feels impossibly distant, not just physically, but conceptually. Above you is not just water, but an enormous column of weight pressing downward. Below you is more water still, stretching into darkness without any visible reference point. By the time you reach 4,000 meters, you're deeper than nearly all parts of the ocean floor. Most of the seafloor lies between 3 and 6 kilometers down, forming vast plains of sediment and slow-moving currents. This region, called the abyssal zone, is cold, dark and stable. Temperatures remain just above freezing. Change happens slowly. Life exists here, but it operates on timescales and energy budgets that feel alien to surface creatures. Humans have sent machines here for decades. Remotely operated vehicles glide across the seabed, lights cutting narrow tunnels through the darkness. Cameras reveal landscapes that look more like deserts than seas, with soft sediments and scattered life. Even here, pressure is immense. Any unprotected structure collapses instantly. Steel, concrete and glass must be carefully engineered to withstand the constant force. And still, the Mariana Trench lies far below this level. The trench is not part of the ordinary seafloor. It is a massive scar in the Earth's crust, formed where tectonic plates collide and one is forced beneath the other. This process, known as subduction, creates a deep, narrow valley that drops sharply from the surrounding terrain. The sides of the trench slope steeply downward, funneling water into a space far deeper than the surrounding ocean. Descending into the trench is different from descending through open water. The walls rise on either side, invisible in the darkness, but present. The sense of enclosure increases even though the space itself is vast. There is a feeling of entering somewhere that does not open outward, but inward. Depth increases rapidly now. 5,000 meters, 7,000, 9,000. Each additional kilometer adds another layer of pressure, another increment of force that no human body could endure. At these depths, numbers become abstract. Pressure reaches levels that can crush hollow objects effortlessly. Materials that feel solid and permanent at the surface behave differently. Metals flex, plastics harden or shatter, lubricants thicken, electronics struggle. Every system must be designed with redundancy, because failure here is not forgiving. There is no margin for error, no gradual warning that something is about to go wrong. The Challenger Deep, the lowest known point in the trench, reaches nearly 11,000 meters below the surface. That distance is difficult to contextualize. If you stacked Mount Everest on top of the seafloor at that location, its peak would still be submerged by more than 2 kilometers of water. The pressure here exceeds 1,000 atmospheres. Every square centimeter experiences a force of over 1,000 kilograms. It is an environment where the concept of down carries far more meaning than it ever does on land. What makes this distance particularly challenging for humans is not just the endpoint, but the journey itself. Depth in the ocean is cumulative. Pressure increases continuously, not in steps. There is no pause, no plateau where conditions stabilize long enough for the body to adjust. Unlike altitude, where humans can acclimate gradually to lower oxygen levels, there is no equivalent adaptation for extreme pressure. Our physiology has no mechanism for becoming comfortable under such conditions. Even in pressurized submersibles, the distance introduces logistical constraints. Descent takes hours. As the vessel sinks, communication with the surface becomes delayed and intermittent. Radio waves do not travel well through seawater, so messages rely on acoustic signals that move slowly and can be disrupted by terrain. The deeper you go, the more isolated you become. The surface world continues as usual, but you are cut off from it, suspended in a vertical corridor of darkness. This isolation has psychological effects as well. Humans are not accustomed to environments where movement is limited, escape is impossible, and failure carries immediate consequences. Inside a deep-sea submersible, space is tight. There is no standing, no walking, no pacing. Every sound matters. Every vibration is noticed. Time stretches in unfamiliar ways, shaped by the steady descent and the knowledge of how far away help would be if something went wrong. Distance also affects energy. Batteries drain. Systems generate heat that must be managed carefully. Too much heat, and equipment fails. Too little, and components freeze or become brittle. The deeper the mission, the more everything depends on precise planning and careful control. Staying longer means carrying more power, more oxygen, more redundancy. Every additional hour adds complexity and risk. This is one reason humans cannot stay long in the Mariana Trench. It's not just that the environment is extreme, it's that maintaining a bubble of survivable conditions becomes increasingly difficult the longer you remain. Supplies are finite, systems degrade, fatigue sets in. Even if the submersible itself remains intact, the humans inside it are subject to stress, confinement, and the subtle strain of knowing they are somewhere the human body fundamentally does not belong. It's also worth noting that the descent itself shapes how the trench is experienced. You don't simply arrive, you sink toward it, slowly, deliberately, watching instruments confirm what your senses cannot. Depth readouts tick upward. Pressure gauges climb. External cameras reveal nothing but blackness punctuated by drifting particles. The sense of motion comes not from visual cues, but from time passing and numbers changing. By the time the bottom is reached, if it is reached at all, the journey has already taken hours. The body has been still for a long time, muscles stiffen, attention narrows, the mind alternates between focus and drift. This is not an environment that invites lingering. Every moment spent at depth increases exposure to risk without offering the kind of reward humans are wired to seek. And yet, we continue to go. Not often, and not casually, but deliberately. Because the distance itself holds meaning. It represents a boundary between what we can inhabit and what we can only observe. The long way down from the surface is not just a physical measurement, it's a reminder of how thin the layer of Earth is that supports our ordinary existence. As we move further into this exploration, it becomes clear that distance and pressure are inseparable here. One creates the other. Every meter downward adds weight, force, and constraint. To understand why humans cannot stay long in the Mariana Trench, we need to understand how that weight accumulates, how pressure builds not as a sudden threat, but as a constant presence that shapes every interaction. So with the surface now far above us, and the trench walls rising silently around us, it's time to look more closely at that invisible force pressing in from all sides, the one factor that defines life at depth more than any other, and quietly sets the limits on how long we can remain. Water doesn't look heavy. At the surface it moves easily. It ripples, splashes and yields to every passing hand. You can push through it, float on it, dive into it, and emerge without feeling like you've wrestled with something particularly forceful. That impression is one of the great illusions of the ocean. Water only seems gentle because we live at the very top of it, beneath a column that is, by comparison, very thin. The moment you begin to descend, that illusion starts to fall apart. Not all at once. There's no sudden signal that says you've crossed a threshold. Instead, the weight of water announces itself gradually, patiently, adding itself layer by layer, meter by meter. Every drop above you contributes to a force that never rests, never fluctuates, and never asks whether you're prepared to carry it. To understand why humans cannot stay long in the Mariana Trench, you have to understand this weight not as an abstract number, but as a physical presence. Water has mass, a lot of it. A single cubic meter of seawater weighs just over a metric ton. That might not sound especially alarming until you realise how many cubic meters are stacked above any given point in the ocean. At 10 meters below the surface, you already have roughly one additional atmosphere of pressure pressing down on you. At 100 meters, it's 10 atmospheres. At 1,000 meters, 100. The relationship is simple and unforgiving. What makes this different from weight on land is that it presses from all directions at once. Gravity pulls downward, but pressure from water pushes inward. Front, back, sides, top, bottom. There is no direction you can lean to escape it, no posture that relieves the load. The water does not crush you downward into the seabed. It compresses you uniformly, squeezing every air-filled space, every flexible structure, every gap that can possibly be made smaller. At shallow depths, the human body handles this surprisingly well. That's because we're mostly made of water ourselves. and water does not compress easily. Solid tissues, fluids, and dense materials are relatively unaffected by moderate pressure changes. The problems arise in the parts of us that are not solid or liquid, the spaces that contain gas, the lungs, the sinuses, the middle ear, the digestive tract. These spaces shrink as pressure increases, and if they are not equalized carefully, they cause pain, injury, or worse. Divers learn to manage this. They equalize pressure in their ears, they control their breathing, they ascend and descend slowly to allow gases to dissolve and re-emerge safely. But this management only works within a narrow range. The deeper you go, the faster pressure increases, and the harder it becomes to maintain balance inside the body. By the time you reach depths measured in kilometers, equalization is no longer relevant. The human body simply cannot function unprotected under that kind of load. The lungs, even if filled with compressed air, would collapse. Blood vessels would struggle to maintain shape. Cells would experience mechanical stress they were never designed to withstand. The weight of water becomes not just uncomfortable or dangerous, but incompatible with life as we know it. Inside a submersible, however, the situation changes. The pressure vessel takes on the burden instead. Thick walls of metal or composite materials hold back the water, maintaining a pocket of near-surface pressure inside. In effect, the vessel carries the weight of the ocean, so the humans inside do not have to. But this does not mean the weight disappears, it is simply transferred. The deeper the vessel goes, the more force presses against its hull. This force is constant. It does not spike or ebb. It presses with the same intensity every second the vessel remains at depth. Engineers design these hulls carefully, often as spheres or near spheres, because that shape distributes stress evenly. Flat surfaces would buckle. Corners would concentrate force. Even tiny imperfections become critical under such pressure. At the depth of the Mariana Trench, the hull of a submersible must withstand pressures exceeding 100 megapascals. That's not a number meant for intuition. What matters is that any weakness, any flaw, any material fatigue can lead to catastrophic failure. And when failure happens under that much pressure, it is instantaneous. There is no gradual leak, no slow warning. The ocean does not rush in. It collapses the space in a fraction of a second. This reality shapes every aspect of deep-sea exploration. It's why missions are short. It's why they are rare. It's why they are planned obsessively. The longer a vessel remains at depth, the longer it must endure that crushing force without relief. Materials behave differently under sustained pressure. Microfractures can grow, seals can weaken, temperature changes can alter structural properties. Time itself becomes a factor in how much weight a structure can carry safely. For the humans inside, the knowledge of this weight is ever present, even if it's not consciously acknowledged. Every creak, every sound of shifting metal, every change in vibration carries meaning. In most environments, humans are accustomed to hearing structures respond to load. Buildings settle, ships flex, bridges hum. But at the bottom of the ocean, those sounds take on a different character. They are reminders that the environment outside is exerting a force beyond anything encountered on land. The weight of water also affects how long systems can operate. Batteries must power life support, lighting, communication, and propulsion. The deeper the vessel, the more energy is required to move against dense water. Heat generated by electronics must be managed carefully. At depth, heat cannot dissipate easily. Too much heat stresses components. Too little, and cold begins to interfere with performance. The weight of water indirectly governs all of this by limiting how robust systems can be before they become too heavy to deploy or too complex to trust. There is another aspect of weight that is less obvious but just as important. Buoyancy. At the surface, buoyancy feels simple. Objects float or sink depending on their density. At extreme depths, buoyancy becomes a delicate balance. A submersible must be heavy enough to descend but buoyant enough to return. This often involves specialized materials that provide lift without compressing under pressure. Designing these systems is challenging, and once again, time matters. Materials that perform well initially may degrade under prolonged exposure to pressure. For a human, staying longer at depth means trusting not just the hull, but every supporting system. Oxygen supply must remain stable. Carbon dioxide must be removed efficiently. Humidity must be controlled. Waste heat must be managed. All of these processes generate internal pressure and require careful regulation. Any imbalance adds stress to the system, and under the weight of the ocean, margins for error shrink. It's also worth considering that pressure does not only act on physical structures, it influences chemistry. Gases dissolve more readily into liquids under high pressure. This is why decompression sickness occurs when divers ascend too quickly. At extreme depths, gas behavior becomes even more complex. Inside a sealed vessel, pressure is controlled, but any failure that allows external pressure to intrude changes conditions instantly. There is no gradual adaptation possible. Life at the bottom of the Mariana Trench has adapted to this weight by eliminating the things that pressure destroys. Many deep-sea organisms have no gas-filled spaces. Their bodies are soft, flexible, and filled with fluids that match the surrounding pressure. Their cellular membranes and proteins are structured to function under compression. For them, the weight of water is not an enemy. It is simply the environment. Humans cannot do this. We cannot remove air from our lungs. We cannot function without pressure differentials in our circulatory system. We cannot alter our cellular machinery to tolerate forces that would disrupt its normal operation. We carry within us assumptions about pressure that are baked into every level of our biology. This is why the weight of water is such a decisive factor. It is not something we can train against or gradually adapt to. We can engineer around it, temporarily, but only within limits. Every additional hour at depth is another hour that materials must resist deformation, that systems must perform flawlessly, that humans must remain alert and functional in a confined space surrounded by overwhelming force. The ocean does not become heavier the longer you stay, but your exposure to its weight accumulates, risk increases, fatigue sets in. Small issues that would be trivial at the surface become serious concerns: a stuck valve, a sensor glitch, a power fluctuation. Under thousands of meters of water, these are not inconveniences, they are potential endpoints. So when we talk about why humans cannot stay long in the Mariana Trench, we are not talking about courage or curiosity, we are talking about physics, about mass and force and time, about an environment whose defining characteristic is a weight that never lets up, never gives ground, and never cares how carefully we prepared. And as we continue downward in this explanation, that weight leads naturally into something even more specific, something the body experiences directly and immediately when exposed, an invisible force that turns mass into pressure and pressure into a limit that no amount of determination can cross. Pressure is one of those forces that is easy to ignore precisely because we live inside it all the time. Right now, as you sit or lie wherever you happen to be, the air above you is pressing down on your body with a force of about 1 atmosphere. That's roughly 10 tons of air resting on every square meter of your surface. It sounds dramatic when you phrase it that way, but it doesn't feel like anything at all. Your body has spent its entire existence under this pressure. It is built for it. Every system inside you assumes it as the default setting. The ocean changes that assumption the moment you leave the surface. Pressure in water behaves differently from pressure in air, not because the rules change, but because water is far denser. Air is light and compressible. Water is heavy and nearly incompressible. As you descend, the amount of water above you increases rapidly, and with it, the force pushing inward on everything you are and everything you bring with you. This force does not announce itself loudly. It doesn't shove or strike. It simply tightens evenly and relentlessly, like a grip that never loosens. At shallow depths, this grip is subtle. A swimmer diving a few meters feels only a mild squeeze in the ears or sinuses. A scuba diver descending further becomes more aware of it, learning to equalize pressure to avoid discomfort or injury. These sensations are the body's early warning system, reminders that the surrounding environment is changing faster than our internal spaces naturally can, but they are still manageable. The grip is firm, not crushing. As depth increases, pressure stops being something you feel and starts being something that defines the environment. By the time you reach 100 meters, the pressure is already 10 times what it is at the surface. At 1,000 meters, it's 100 times. There is no point at which it stabilizes. It never plateaus. Every additional meter adds more force, and because the ocean is so deep, that addition continues far beyond anything humans can tolerate directly. The key thing to understand about pressure is that it doesn't target specific weaknesses selectively. It applies itself everywhere at once. If there is a surface, pressure pushes on it. If there is a cavity, pressure tries to collapse it. If there is a flexible boundary, pressure deforms it. This is why pressure is so dangerous. There is no single place you can reinforce and call it done. Everything must hold, all the time. The human body is not designed for this. Our internal structures rely on differences in pressure to function. Blood flows because pressure is higher in some vessels than others. Breathing works because pressure differences allow air to move in and out of the lungs. Hearing depends on delicate membranes responding to tiny pressure changes. Even at the cellular level, pressure gradients help regulate the movement of ions and molecules across membranes. Under extreme external pressure, these gradients are overwhelmed. The balance that keeps systems running smoothly begins to break down. Gas-filled spaces shrink. Fluids shift. Tissues compress. At a certain point, function gives way to failure, not because anything dramatic happens, but because nothing can continue operating as designed. This is why unprotected exposure to deep-sea pressure is immediately fatal. There is no dramatic implosion of the human body, despite what movies often suggest. Instead, the lungs collapse, blood chemistry changes, and vital organs are disrupted faster than consciousness can respond. It is not violent in a cinematic sense. It is absolute. Inside a pressure-resistant vessel, humans are shielded from this direct effect. The interior remains at or near surface pressure, allowing bodies to function normally. But the pressure has not gone away. It has simply been relocated to the outside of the hull. And this is where the ocean's grip becomes mechanical rather than biological. Every deep-sea submersible is essentially a container-resisting collapse. Its walls exist to hold back the ocean. The deeper it goes, the harder the ocean squeezes. This squeezing is uniform, but the structure resisting it must be flawless. A microscopic crack, an imperfect weld, a material defect that would be insignificant on land becomes a potential point of failure under extreme pressure. Engineers account for this by overbuilding. Hulls are thick, shapes are rounded, materials are chosen for their ability to deform slightly without breaking. Safety margins are built in. But safety margins are not infinite. They are calculated based on expected loads, expected durations, and expected behavior of materials under stress. Pressure introduces a time component to risk. A structure might withstand a given pressure for a short period without issue, but prolonged exposure increases the chance of fatigue. Metals experience creep, a slow, permanent deformation under constant load. Seals can compress and lose elasticity. Interfaces between materials can shift microscopically. None of this happens quickly or dramatically, but all of it matters when the surrounding force never relents. This is one reason humans cannot stay long in the Mariana Trench. Even if a submersible can reach the bottom safely, staying there means subjecting every component to sustained maximum stress. The longer the stay, the more opportunities for small problems to grow. Deep-sea missions are not limited by curiosity or willingness. They are limited by probabilities. Pressure also affects how systems behave internally. Electronics generate heat, and that heat must be dissipated. At depth, the surrounding cold water acts as a heat sink. But pressure alters thermal conductivity and material properties. Lubricants behave differently. Plastics can become brittle. Rubber seals stiffen. Components that function reliably at the surface may behave unpredictably when compressed for hours under enormous force. The ocean's grip is not static either. Currents exist even at depth, slow but persistent. A submersible resting on the seafloor may experience subtle shifts in orientation. These shifts translate into changing stress patterns across the hull. Again, nothing dramatic, but enough to matter when everything is already operating near its limits. For the humans inside, pressure manifests indirectly as confinement and awareness. There is no window you can open, no door you can test. The hull is either holding or it isn't. This creates a psychological environment where trust in engineering is absolute. You're not negotiating with nature. You're relying on layers of design, calculation and testing to keep an invisible force at bay. This trust has limits. Humans can remain calm and focused for a time, but extended exposure to high-risk environments increases stress, even if nothing visibly goes wrong. The body responds to sustained alertness with fatigue. Decision-making slows. Small discomforts become magnified. In a place where error tolerance is low, this matters. Pressure also shapes how movement is possible. At extreme depths, submersibles move slowly. Rapid changes in direction or speed place additional stress on the hull and propulsion systems. Thrusters must work against dense water while maintaining stability. Precision matters more than speed. This further limits how much can be accomplished during a single dive, making long stays less practical. Then there is the matter of ascent. Pressure is just as relevant on the way back up. Although the interior of a submersible remains pressurized, external pressure decreases as it rises. Structural stresses change. Materials that have been compressed begin to relax. This transition must be managed carefully. Rapid ascent introduces its own risks, both mechanical and operational. In contrast, deep-sea organisms experience none of this conflict. Their bodies are in equilibrium with their environment. Pressure inside and outside is equal. There is no hull resisting collapse, no stress concentration, no time limit imposed by material fatigue. They exist comfortably where we can only visit briefly. This difference highlights something important. Pressure is not inherently hostile. It is only hostile to things not designed for it. The ocean's invisible grip feels oppressive to us because it contradicts our biological expectations. For creatures evolved to live there, it is simply normal. Humans cannot change their expectations at a fundamental level. We cannot re-engineer our organs to function without pressure differentials. We cannot remove our reliance on gas exchange or rigid structures. The best we can do is build temporary shelters that hold the ocean at arm's length, and those shelters come with clocks attached. Every minute spent at depth is a minute that the ocean presses inward, testing materials, systems, and assumptions. There is no safe way to forget about pressure while you're there. It defines the experience from beginning to end. As we continue deeper into this question, pressure leads us naturally to the human body itself. Because while engineering can resist pressure for a time, biology has far stricter limits. The ocean's grip does not need to break steel to defeat us. It only needs to interfere with the fragile balance that keeps a human body working as intended. The human body is often described as adaptable, and in many ways that's true. We can survive in hot climates and cold ones. We can live at sea level or on high plateaus. We can endure hunger, fatigue, injury and illness with a resilience that has allowed our species to spread across nearly every surface of the planet. But all of that adaptability exists within a very specific set of assumptions. The body expects certain things from Earth, and it expects them so consistently that we rarely notice them at all. One of those expectations is stability. Not emotional stability or social stability, but physical stability. The kind that comes from standing on solid ground under a predictable sky, with gravity pulling in one direction and pressure applied evenly from the air around us. From the moment we're born, every cell in our body develops in response to those conditions. Bones grow dense enough to support our weight under one gravity. Muscles strengthen to move against that same constant pull. Blood vessels form with walls thick enough to handle a known range of pressures. Organs settle into positions shaped by gravity and supported by surrounding tissues that behave in familiar ways. We don't think of gravity and atmospheric pressure as environmental conditions in the same way we think of temperature or weather, but biologically, they are just as important. They are the background settings against which everything else operates. Remove or alter them too much, and the body doesn't simply adjust, it begins to malfunction. Take breathing, for example. Breathing feels automatic because it is, but it depends on a precise relationship between the pressure inside your lungs and the pressure outside your body. When you inhale, your diaphragm moves, expanding your chest cavity and lowering the pressure inside your lungs. Air flows in because the pressure outside is higher. When you exhale, the process reverses. This works effortlessly because the surrounding air pressure stays within a narrow expected range. Change that range dramatically, and the system struggles. At high altitude, where atmospheric pressure is lower, breathing becomes less efficient. Oxygen enters the bloodstream more slowly. The body compensates by increasing breathing rate, heart rate, and red blood cell production. Even then, there are limits. Go high enough, and acclimatization fails. In the deep ocean, the problem is inverted. External pressure increases rather than decreases. Gas behaves differently. The lungs cannot simply expand or contract as designed. Without protection, they collapse. The entire breathing mechanism depends on conditions that no longer exist. This is not a flaw in the body. It is a consequence of how tightly optimized it is for life at the surface. The circulatory system carries similar assumptions. Blood flows because the heart creates pressure differences, pushing blood through arteries and allowing it to return through veins. Valves ensure one-way flow. Capillaries allow exchange of oxygen, nutrients, and waste. All of this relies on vessel walls that are flexible but not too flexible, strong but not rigid. They are tuned to operate under one atmosphere of external pressure. Increase external pressure dramatically, and those balances are disrupted. Vessels may compress. Flow patterns change. The heart must work against altered resistance. Even if the body is shielded inside a pressurized environment, prolonged stress, confinement, and altered sensory input place strain on systems that evolved for movement, variation, and open space. The nervous system also expects Earth to behave a certain way. Nerve signals travel through electrochemical gradients that are sensitive to temperature, pressure, and chemical composition. Sensory organs interpret signals based on patterns developed over millions of years. Vision expects light. Hearing expects vibrations through air. Balance relies on gravity, acting consistently on fluid-filled structures in the inner ear. In the Mariana Trench, most of these inputs are absent or distorted. There is no natural light. Sound behaves differently in dense water and through metal hulls. Movement is minimal. Gravity is still present, but orientation loses meaning when there is no up or down relative to the environment. Over time, this sensory deprivation affects cognition, mood, and alertness. Then there is temperature regulation. The human body maintains a narrow internal temperature range. Too hot or too cold, and enzymes stop working efficiently. Heat production and heat loss are balanced constantly through blood flow, sweating, shivering, and behavioral adjustments like seeking shelter or changing posture. On land, this balance is relatively easy to maintain. In water, especially cold water, heat loss accelerates. Water conducts heat away from the body far more efficiently than air. Even in a pressurized vessel, temperature control must be actively managed. Failure to do so affects comfort first, then performance, then safety. Another expectation the body has is space. Not just physical space, but the ability to move. Muscles, joints, and connective tissues are designed to be used regularly. Prolonged immobility leads to stiffness, reduced circulation, and fatigue. In extreme cases, it can contribute to blood clots, muscle atrophy, and joint pain. Deep-sea submersibles are necessarily small. They are designed to minimize surface area and maximize structural integrity. This leaves little room for movement. Occupants sit or crouch for hours at a time. There is no stretching, no walking, no change in posture beyond small adjustments. Over a short period, this is tolerable. Over longer periods, it becomes physically taxing. The digestive system also operates under assumptions. It expects regular meals, hydration, and a gravity-assisted process for moving food through the intestines. Stress, altered schedules, and confinement disrupt appetite and digestion. Nausea is common in unusual environments, whether in space, at sea, or underwater. Discomfort may seem minor, but in a high-risk environment, even small physiological stresses matter. Psychologically, the body and mind expect a certain relationship with time and environment. We're used to cycles of light and dark. We're used to horizons, distances, and reference points. We're used to knowing, instinctively, that help is not impossibly far away. In the Mariana Trench, those assumptions collapse just as thoroughly as unprotected lungs would. Inside a submersible, the body may be physically safe from pressure, but it is not in an environment it recognizes as livable. Stress hormones rise, attention narrows, fatigue accumulates. These are not signs of weakness. They are normal responses to conditions that fall outside the range of human expectation. It's important to understand that none of this means humans are fragile in a general sense. It means we are specialized. We're exquisitely adapted to a thin layer of Earth's surface, a narrow band of pressure, temperature, gravity, and chemistry. That specialization is what allows us to function so efficiently here, but it comes at the cost of versatility in extreme environments. Life at the bottom of the Mariana Trench evolved under very different expectations. Those organisms do not rely on gas-filled spaces. They do not need light. Their proteins are structured to function under compression. Their metabolisms are slow, conserving energy in a place where food is scarce. They do not fight the environment. They match it. Humans, by contrast, must constantly fight the environment to remain there at all. Every breath, every heartbeat, every moment of awareness depends on systems maintaining conditions that the surrounding world does not provide. This effort can be sustained for a while with technology, planning, and discipline, but it cannot be sustained indefinitely. The longer a human stays in an environment that violates these expectations, the more strain accumulates. Not always dramatically, often quietly. A little more fatigue, a little less focus, a little more discomfort. In a place like the Mariana Trench, those small changes matter because there is no margin for error. Understanding what the human body expects from Earth helps clarify why some places remain beyond our ability to inhabit. We can visit them, we can observe them, we can learn from them. But staying requires compatibility, not just curiosity. And as we move forward, that mismatch becomes even clearer when we focus on one of the body's most basic requirements, something so automatic we rarely think about it at all, until the environment makes it impossible to take for granted. Breathing is so automatic that it rarely enters conscious thought. It happens while we sleep, while we speak, while we focus on something else entirely. You can hold your breath for a moment if you choose to, but even that is temporary. Eventually the body overrides intention and pulls air back in. This is not a habit. It is a requirement so fundamental that nearly every other system depends on it continuing without interruption. On the surface of Earth, breathing works because the environment cooperates. The air around us contains oxygen at a concentration our lungs are built to extract. The pressure of that air is high enough to push oxygen into the bloodstream, but not so high that it damages tissue. The gases we inhale and exhale behave predictably. Every part of the process assumes that the surrounding world will stay within certain boundaries. The deep ocean violates nearly all of those assumptions at once. To understand why breathing becomes such a serious problem in the Mariana Trench, it helps to look at what breathing actually involves beyond the simple idea of air going in and out. When you inhale, oxygen travels down your airway into millions of tiny sacs in your lungs called alveoli. These sacs are thin-walled and surrounded by capillaries. Oxygen passes through the alveolar walls into the blood, while carbon dioxide passes out of the blood and into the lungs to be exhaled. This exchange works because of pressure differences and because gases behave in predictable ways at surface conditions. Pressure is the first issue. As external pressure increases, gases compress. If a human were exposed directly to the pressure found thousands of meters underwater, the air spaces in the lungs would collapse almost immediately. The alveoli would not be able to remain open. There would be no space for gas exchange to occur. Even if oxygen was somehow present, there would be no functional mechanism to use it. This is why unprotected humans cannot survive at depth, even briefly. It is not a matter of drowning in the traditional sense. It is a mechanical failure of the respiratory system. The lungs are simply not designed to function when the surrounding pressure exceeds their structural limits. In shallow diving, this problem is managed by breathing compressed air. As a diver descends, the air supplied to them is delivered at the same pressure as the surrounding water. This keeps the lungs inflated and prevents collapse. But this solution creates new problems as depth increases. One of those problems is gas toxicity. Air is mostly nitrogen, with oxygen making up about 21%. At surface pressure, nitrogen is inert. It does not interfere with nerve function or consciousness. Under high pressure, nitrogen dissolves into the bloodstream and tissues more readily. At certain depths, this dissolved nitrogen begins to affect the nervous system, causing a condition known as nitrogen narcosis. Nitrogen narcosis impairs judgment, coordination and perception. It can cause euphoria, confusion and delayed reactions. At greater depths, it can lead to hallucinations and loss of consciousness. This effect limits how deep divers can safely go while breathing air. Even with careful training, it becomes dangerous long before reaching the depths of the Mariana Trench. Oxygen itself also becomes a problem under pressure. While oxygen is essential for life, too much of it can be harmful. At high partial pressures, oxygen becomes toxic. It can damage lung tissue, irritate airways, and, more dangerously, trigger seizures. Oxygen toxicity sets strict limits on how much oxygen can be safely present in breathing mixtures at depth. To mitigate these issues, deep divers use specialized gas mixtures. Helium replaces much of the nitrogen because it is less narcotic. Oxygen concentration is carefully reduced to avoid toxicity. These mixtures allow divers to go deeper than they otherwise could, but even with these adjustments, human diving depths are extremely limited compared to the depth of the Mariana Trench. At the depths we are discussing, breathing gas directly is no longer feasible at all. The pressures are simply too high. No breathable mixture can function safely in open contact with the human lungs. This is why humans who go to extreme depths must do so inside sealed, pressurized vessels. Inside a submersible, breathing returns to something closer to normal, but the situation is still not trivial. The air inside the vessel must be carefully controlled. Oxygen levels must remain within a narrow range. Carbon dioxide, which we exhale continuously, must be removed efficiently. If carbon dioxide accumulates, it can cause headaches, confusion, rapid breathing, and eventually loss of consciousness. Carbon dioxide buildup is one of the most serious risks in enclosed environments. Unlike oxygen depletion, which can be gradual and subtle, elevated carbon dioxide can affect cognition quickly. Scrubber systems remove carbon dioxide from the air, often using chemical reactions. These systems must function flawlessly for the duration of the mission. Any failure becomes immediately dangerous. Humidity is another concern. breathing releases moisture into the air. In a small sealed space, humidity can rise quickly. Excess moisture affects comfort, equipment, and air quality. Condensation can interfere with electronics. Mold and microbial growth become concerns during longer missions. All of this must be managed with limited power and space. Breathing also interacts with temperature control. Every breath carries heat and moisture. In a deep-sea environment, where external temperatures are near freezing, maintaining a comfortable internal temperature requires constant energy. Too cold and breathing becomes shallow and inefficient. Too warm and fatigue increases. There is also the psychological aspect of breathing in confined, high-risk environments. Humans are sensitive to air quality, even when they cannot articulate why. A slightly stale atmosphere, a faint chemical odour from scrubbers, or a subtle change in airflow can trigger discomfort or anxiety. This response is not irrational. It reflects the importance of breathing to survival. Extended periods of breathing recycled air can contribute to fatigue and irritability. Even if oxygen and carbon dioxide levels remain technically safe, the lack of freshness affects perception. In an environment where concentration and calm decision-making are essential, these effects matter. Another factor is the simple act of breathing under stress. Stress changes breathing patterns. People breathe faster or more shallowly. This alters carbon dioxide levels in the blood, which can lead to lightheadedness or increased anxiety. In a deep-sea submersible, where movement is limited and stakes are high, managing stress becomes part of managing respiration. Emergency scenarios make the problem more acute. If a system fails and oxygen levels drop or carbon dioxide rises, there is little room for error. There is no fresh air to draw from. Every breath depends on machinery. This dependency shapes mission duration. The longer the stay, the greater the cumulative risk of a respiratory system failure. Contrast this with life on the surface, where breathing problems are usually temporary and solvable. Step outside, open a window, take a deeper breath. In the Mariana Trench, there is no outside air. There is only the environment inside the vessel and the crushing pressure outside it. This reliance on artificial breathing conditions also limits how many people can be present. More people mean more oxygen consumption and more carbon dioxide production. Submersibles designed for extreme depths typically carry very few occupants, sometimes only one or two. Increasing capacity increases complexity and risk. Breathing also ties into decompression considerations. While occupants of a pressurized submersible do not experience decompression sickness in the same way divers do, any change in internal pressure must be managed carefully. Rapid changes can affect ears, sinuses, and lungs. Systems are designed to avoid this, but it adds another layer of constraint. The fundamental issue is that breathing, which feels effortless and limitless on land, becomes a tightly managed resource at depth. Every breath is accounted for. Every molecule of oxygen and carbon dioxide is tracked, processed, and controlled. This level of management is sustainable only for limited periods. Deep-sea organisms do not face this problem. Many extract oxygen directly from water using gills. Their metabolic rates are low. They require far less oxygen than humans do. Their bodies are designed to operate under constant pressure without air-filled spaces. Breathing, for them, is not a struggle against the environment. It is part of it. Humans cannot replicate this biology. We cannot switch to extracting oxygen from water. We cannot slow our metabolism enough to make oxygen needs trivial. We cannot remove our reliance on lungs without ceasing to be human in any meaningful sense. So when breathing becomes a problem in the Mariana Trench, it is not because the environment is actively hostile. It is because it removes the conditions that breathing depends on. It takes something we assume will always be available and turns it into a fragile engineered process with strict limits. Those limits, combined with pressure, confinement, and system reliability, are one of the clearest reasons humans cannot stay long at the deepest points of the ocean. Breathing can be supported there, but only temporarily, only carefully, and only with constant attention. And as breathing becomes more difficult to guarantee over time, other aspects of the environment begin to press in as well, not just physically, but perceptually, as cold, darkness, and isolation start to shape how long the human body and mind can remain functional at all. Cold does not arrive suddenly in the deep ocean. It does not rush at you or announce itself with a dramatic change. Instead, it settles in gradually, becoming more noticeable as everything else fades away. Near the surface, water temperature varies with weather, latitude, and season. Warm currents mix with cooler ones. Sunlight transfers energy into the upper layers. There is motion, variation, and a sense of change. But as depth increases, those variations disappear, and temperature begins to stabilize in a way that is both predictable and unforgiving. By the time you descend a few hundred meters, the warmth of the surface is already gone. The water grows steadily colder, approaching a narrow range just above freezing. Below a certain depth, this temperature barely changes at all. It doesn't matter whether it is day or night above, summer or winter, calm or stormy. The deep ocean exists in a permanent cold, one that does not fluctuate and does not respond to surface conditions. It is a cold that persists year after year, century after century, without interruption. For humans, cold is not just uncomfortable. It is a physiological challenge. The human body generates heat constantly as a byproduct of metabolism, and it loses heat to its surroundings. On land, heat loss occurs mostly through air, which is a relatively poor conductor. In water, heat loss accelerates dramatically. Water pulls heat from the body far more efficiently than air ever could. This is why even moderately cool water can become dangerous over time, and why immersion in cold water leads to hypothermia much faster than exposure to cold air. Inside a deep-sea submersible, direct contact with cold water is avoided, but the environment outside still matters. The surrounding water acts as a massive heat sink. Any heat generated inside the vessel naturally wants to move outward, through the hull, into the colder environment beyond. Maintaining a stable internal temperature requires continuous energy input and careful insulation. If heating systems fail or power becomes limited, the temperature inside the vessel begins to drop. Cold affects the human body in layered ways. Initially, it reduces comfort. Fingers feel stiff, muscles tighten, movement becomes less fluid. Over time, cold slows nerve conduction, dulling sensation, and reducing coordination. Shivering may occur as the body attempts to generate heat, but shivering consumes energy and increases oxygen demand, which in a sealed environment creates additional strain on life support systems. As exposure continues, cognitive effects emerge. Cold reduces mental sharpness, decision-making slows, reaction times increase. Even mild hypothermia can impair judgment, which is especially dangerous in an environment where clear thinking is essential. These effects do not require extreme cold to appear, they simply require sustained exposure to temperatures below the body's comfort zone. The darkness of the deep ocean compounds this problem in a different way. Darkness at depth is not the same as darkness on land. It is not a lack of light caused by nightfall that will eventually reverse itself. It is a permanent condition. Sunlight cannot penetrate more than a few hundred meters into the ocean. Beyond that, there is no natural light source at all. This absence of light changes how the brain processes information. Human vision is a dominant sense. We rely on it for orientation, movement, and awareness. In darkness, especially complete darkness, the brain receives far less information about the surrounding environment. This forces other senses to compensate, but in a confined, artificial space, those senses are also limited. Inside a submersible, artificial lighting restores visibility, but it does not recreate a natural visual environment. The light is narrow, focused, and often harsh. Outside the windows, if windows exist at all, there is usually nothing to see beyond a small illuminated area. There is no horizon, no distant reference point, no sense of scale. The outside world becomes a black void punctuated occasionally by drifting particles or brief flashes of bioluminescence. This lack of visual context affects time perception. On the surface, we subconsciously track time through environmental cues, the movement of the sun, changes in light intensity, shadow shifting. Even artificial environments tend to mimic these cycles, with lights turning on and off according to schedules. In the deep ocean, these cues are absent. Time begins to feel detached from the environment. Minutes can stretch or compress unpredictably. Without windows showing daylight or darkness, the mind relies entirely on clocks and routines to maintain a sense of sequence. If attention drifts, time can lose its usual structure. This effect is subtle at first, but over hours it becomes more noticeable. Cold contributes to this distortion. When the body is slightly chilled, it tends to conserve energy. Movement decreases. The urge to remain still increases. This physical slowing influences mental pacing. Thoughts may become quieter, but they may also become less organized. Fatigue sets in not because of exertion, but because maintaining alertness requires more effort under these conditions. Darkness also influences mood. Prolonged absence of natural light is associated with changes in neurotransmitter activity, including serotonin and melatonin regulation. On the surface, this effect is seen in environments with long winters and limited daylight. In the deep ocean, the absence of light is total and unchanging. Although submersibles use artificial lighting to mitigate this, the light does not replicate the full spectrum or intensity of sunlight, and it does not provide the same psychological signals. This contributes to a sense of isolation that goes beyond physical confinement. It is not just that the space is small, it is that the environment offers no variation, no reassurance, no external rhythm. The world outside the vessel is silent, dark, and indifferent. For humans, who evolved in environments filled with sensory information, this can be mentally taxing. The absence of time cues also affects sleep. The body's circadian rhythm depends heavily on light exposure to regulate cycles of alertness and rest. Without clear signals, the rhythm can drift. People may feel sleepy at unexpected times, or alert when they should be resting. In a short mission, this may not be a major issue. Over longer periods, it disrupts performance and well-being. Managing sleep in a deep-sea environment is complicated by space constraints and noise. Submersibles contain machinery that hums, vibrates, and cycles on and off. These sounds are constant, and while occupants may acclimate to them, they still interfere with rest. Sleeping positions are limited. True rest is difficult to achieve. Cold further complicates sleep. The body naturally lowers its core temperature slightly during sleep, but if the environment is already cool, this can lead to discomfort or excessive heat loss. Maintaining a balance requires active temperature regulation and careful planning. All of this contributes to a subtle erosion of endurance, not a dramatic failure, but a gradual narrowing of tolerance. Each hour spent in cold, dark isolation adds a small amount of strain. Alone, each factor might be manageable. Together they limit how long humans can remain functional, focused, and safe. For deep-sea organisms, these conditions are not stressors. Cold is normal. Darkness is expected. Time, as humans perceive it, is irrelevant. Many deep-sea species have slow metabolisms and long lifespans. They are not driven by daily cycles. Their activity patterns are governed by food availability and chemical cues rather than light and temperature changes. Humans cannot adopt this mode of existence, even temporarily. Our metabolism is relatively fast. Our brains demand constant input. Our bodies are tuned to cycles and variation. When those cycles disappear, we do not simply slow down to match the environment. We experience strain. The absence of time cues also affects communication with the surface. Messages sent acoustically take time to travel. Conversations are delayed. There is no real-time interaction. This separation reinforces the feeling of being removed from the normal flow of events. The world above continues, but you're not participating in it directly. This psychological distance matters. Humans are social creatures. Even when physically alone, we rely on the knowledge that others are nearby or reachable. In the Mariana Trench, that knowledge is abstract. Rescue is not immediate. Assistance is not close. This awareness adds another layer of mental load. Cold, darkness, and the absence of time do not cause immediate failure. They do not crush or suffocate. Instead, they reshape the human experience in ways that reduce resilience over time. They make small problems feel larger. They reduce margins for error. They turn what might be an interesting challenge into a sustained test of endurance. This is one of the reasons deep-sea missions are brief. Not because humans cannot endure discomfort, but because extended exposure to these conditions increases the likelihood of mistakes, fatigue, and system stress. In an environment where error tolerance is low, this is not acceptable. As we continue to examine why humans cannot stay long in the Mariana Trench, these environmental factors lead naturally into another limitation, one that becomes unavoidable when the senses are deprived and the environment offers no familiar anchors. The fragile internal balance that keeps the human body and mind working smoothly begins to shift, and once that balance is disturbed, staying longer becomes less about curiosity and more about risk. Light feels so constant in everyday life that it's easy to forget how fragile it actually is. We wake up to it, move through it, work under it, and rarely stop to consider how specific the conditions are that allow it to exist around us at all. On land, light seems generous. It fills rooms, spills across landscapes, bounces off clouds and buildings, and follows us almost everywhere we go. Even at night, artificial light steps in to replace what the sun withdraws. The world rarely feels truly dark. The ocean tells a very different story. From the moment sunlight touches the surface of the sea, it begins to lose strength. Water is not transparent in the way air is. It absorbs, scatters, and filters light with quiet efficiency. What reaches the surface does not travel freely downward. It is gradually dismantled, wavelength by wavelength, until nothing remains. This process begins almost immediately. The uppermost layer of the ocean, where waves and wind mix the water, is still bright enough to resemble the world above. Sunlight penetrates easily here, and photosynthesis thrives. Phytoplankton float near the surface, forming the foundation of the marine food web. Fish rely on sight. Colours are vivid. The ocean feels alive and familiar, but depth changes that quickly. Light behaves as a form of energy, and water absorbs energy extremely well. As sunlight travels downward, its photons collide with water molecules, suspended particles, and dissolved substances. Each collision steals a little energy. Over distance, those losses add up. The longer the path through water, the more light is removed from the beam. Different wavelengths of light are absorbed at different rates. Red light, which has longer wavelengths and lower energy, disappears first. Within just a few meters, reds are gone. Objects that appear red at the surface look grey or black as soon as you descend slightly. Orange and yellow follow not long after. Green persists a bit deeper, but eventually it too fades. Blue light, with its shorter wavelength and higher energy, travels the farthest. This is why the ocean appears blue from above, and why the last traces of natural light at depth are always blue. Even blue light, however, has its limits. By around 200 meters, sunlight has weakened to the point where photosynthesis becomes impossible. This boundary is known as the photic zone, and it marks a fundamental division in the ocean. Above it, life can rely directly or indirectly on sunlight. Below it, life must find other sources of energy. Beyond this depth, light does not vanish suddenly. It thins, becoming dim and diffuse. Shadows soften. Contrast disappears. Shapes blur. Eventually, even blue light fades away, leaving only darkness. By 1,000 meters, sunlight is effectively gone. Not dim, not twilight. gone. No amount of waiting will bring it back. No change in weather above will alter the condition below. The darkness is permanent, uninterrupted, and absolute. This is why light never reaches the bottom of the Mariana Trench. Not because the trench is uniquely deep, although it is, but because the ocean absorbs light completely long before the seabed comes into view. The trench lies far beyond the point where sunlight can survive the journey downward. The depth of the trench simply ensures that this darkness is total and inescapable. 11 kilometres of water stand between the surface and the bottom. That is an enormous distance for light to travel through a medium designed at the molecular level to absorb it. This absence of light has profound implications for humans. Vision is our primary sense. We rely on it to understand space, movement, and danger. Light provides context. It tells us where we are, what surrounds us, and how far away things might be. When light is removed, that entire framework collapses. In the deep ocean, human vision becomes useless without artificial assistance. Submersibles carry powerful lights that carve narrow cones of visibility into the darkness. These lights reveal only what lies immediately ahead. Everything else remains invisible. The world outside the beam does not gradually fade into shadow. It simply does not exist to the eye at all. This limited visibility affects perception. Without a horizon or distant landmarks, depth and scale become difficult to judge. A small object close to the window can appear larger than it is. A large object just beyond the light's reach may never be seen. Movement is hard to interpret. A drifting particle can resemble a creature. A slow-moving organism can appear stationary until it suddenly shifts. This sensory uncertainty adds mental strain. The brain is constantly trying to interpret incomplete information. It fills in gaps, sometimes incorrectly. Over time, this increases fatigue and reduces confidence in perception, especially in an environment where accurate interpretation matters. The absence of light also alters time perception. On the surface, light provides a continuous signal of time passing. Morning light differs from afternoon light. Shadows move. The colour of the sky changes. Even indoors, artificial lighting often follows daily rhythms. These cues help regulate alertness, mood, and biological cycles. In the deep ocean, none of this exists. Artificial lighting remains constant unless deliberately adjusted. There is no dawn or dusk, no gradual transition. Time becomes something measured only by instruments and schedules, not by experience. For short periods, this is manageable. Over longer periods, it becomes disorienting. Light also plays a role in psychological comfort. Humans associate light with safety and darkness with uncertainty. This is not purely cultural, it is rooted in evolution. Darkness reduces visibility, making it harder to detect threats. Even in a secure environment, prolonged darkness can increase stress levels and vigilance. Inside a submersible, occupants are safe from immediate danger, but the environment does not feel reassuring. Outside the lights, the ocean is invisible and vast. The mind knows that thousands of meters of water press in from all sides, even if the eyes cannot see it. This knowledge, combined with darkness, contributes to a persistent background tension. The darkness of the trench is not empty, however. It is alive in ways that are unfamiliar to us. Many deep-sea organisms produce their own light through bioluminescence. Chemical reactions within their bodies generate flashes, glows, or pulses of light. This light serves many purposes. It can attract prey, confuse predators, or help individuals recognize one another. In the absence of sunlight, bioluminescence becomes a primary means of communication. For humans observing from a submersible, these flashes can be startling. A sudden burst of light appears where there was nothing moments before, then vanishes again. Without context, these events feel unpredictable. They reinforce the sense that the environment operates by rules different from those at the surface. Artificial light also has consequences for the ecosystem. Many deep-sea organisms are sensitive to light. Bright illumination can startle or disrupt them. Some retreat, others behave differently. This means that extended human presence with lights on alters the environment being observed. Staying longer increases this disturbance, which is another reason visits are brief. From a technical standpoint, light requires energy. Powerful lights capable of penetrating murky water consume significant power. In a submersible, power is a finite resource. Every watt used for lighting is a watt not available for propulsion, communication, or life support. Managing this balance limits how long lights can remain on at full intensity. Lights also generate heat. In an environment where temperature must be carefully controlled, this adds another layer of complexity. Excess heat must be dissipated. Insufficient heat leaves occupants cold. The deeper the mission, the more tightly these variables must be managed. The absence of light also affects navigation. On land or near the surface, visual landmarks aid orientation. In the trench, navigation relies entirely on instruments, sonar, depth sensors, inertial navigation systems. These tools work well, but they require constant attention and calibration. Any error accumulates over time. Longer stays increase the chance of drift, misalignment, or sensor error. Without visual confirmation, small discrepancies can go unnoticed until they become significant. This is another subtle reason why time at depth is limited. For the human mind, light represents openness. Darkness represents enclosure, even in vast spaces. The Mariana Trench is enormous, yet it feels closed because it cannot be seen. The walls of the trench may be kilometers away, but psychologically the darkness presses inward, making the space feel smaller than it is. This effect compounds with confinement inside the vessel. The physical space is small. The visible space outside is smaller still. Over time, this compresses perception and attention. The mind narrows its focus, which can be useful for tasks but draining over long durations. Deep-sea organisms do not experience this absence of light as deprivation. They evolved without it. Their senses are tuned to pressure, chemical gradients, and vibration. Light, when it exists at all, is brief and purposeful. For them, darkness is not a lack. It is the default state. Humans cannot easily adopt this perspective. Our sensory systems continue to expect visual information even when it is unavailable. The brain continues to search for cues that are not there. This creates a constant low-level demand on attention. When light never reaches the bottom, it marks more than a physical boundary. It marks a sensory boundary. Beyond it, the environment no longer supports the way humans naturally perceive the world. Technology can compensate, but only partially, and only temporarily. As missions extend, the cumulative effects of darkness, limited visibility, and sensory deprivation add to the strain already imposed by pressure, cold, and confinement. None of these factors alone make staying impossible. Together they tighten the limits. And as the environment strips away light, it also strips away another assumption humans carry with them. The idea that the body's internal balance will remain stable simply because we are alive. In the trench, even that balance becomes fragile, shaped by forces we cannot see and conditions we cannot ignore. The human body gives the impression of stability. We wake up, move through the day, eat, think, sleep, and repeat the cycle with remarkable consistency. Heart rate rises and falls. Blood chemistry stays within narrow limits. Temperature holds steady. Most of the time, all of this happens without conscious effort. We don't monitor it. We don't manage it minute by minute. The balance holds because the environment supports it. That balance is far more delicate than it feels. Inside the body, thousands of processes are constantly adjusting to keep conditions within survivable ranges. Oxygen levels, carbon dioxide levels, blood pH, electrolyte concentrations, hydration, blood pressure, hormone release. None of these are fixed. They fluctuate slightly throughout the day, responding to activity, stress, food intake, and rest. What keeps them from drifting too far is a network of feedback systems that evolved under very specific conditions on Earth's surface. The deep ocean removes many of the assumptions those systems rely on. Take blood chemistry. The pH of human blood must stay within a very narrow window. Even small deviations can impair enzyme function, disrupt cellular processes, and affect consciousness. The body maintains this balance through respiration and kidney function. Carbon dioxide levels in the blood are tightly regulated because carbon dioxide dissolves into carbonic acid, lowering pH. Breathing faster removes carbon dioxide. Breathing slower allows it to accumulate. In a sealed environment like a deep-sea submersible, this regulation becomes indirect. The air you breathe is no longer part of a vast, self-correcting atmosphere. It is a limited system. Carbon dioxide scrubbers must remove what your body produces. Oxygen must be replenished or conserved. Any inefficiency shifts the balance inside you, even if the change is subtle at first. Stress compounds this problem. Stress hormones like cortisol and adrenaline alter breathing patterns, heart rate, and metabolism. You may breathe more shallowly or more rapidly without realizing it. This changes carbon dioxide exchange and can push blood chemistry toward imbalance. On the surface, the body compensates easily. In a confined, controlled environment, compensation has limits. Fluid balance is another fragile system. The human body depends on precise distribution of fluids between cells, blood vessels, and tissues. This distribution is influenced by gravity, pressure, salt levels, and hormone signaling. On land, gravity helps pull fluids downward, and the body adapts to that. In environments where movement is restricted and posture remains constant for long periods, fluid shifts occur. In deep-sea submersibles, occupants often remain seated or crouched for hours. Movement is minimal. Over time, fluids redistribute in ways the body does not expect. Swelling can occur. Circulation becomes less efficient. This may not be dangerous in the short term, but it contributes to discomfort and fatigue, which in turn affect alertness and decision-making. Temperature regulation, already challenged by the cold environment outside, also interacts with internal balance. If the body becomes slightly too cold, metabolic processes slow. If it becomes too warm, dehydration increases and heart rate rises. Both conditions place additional demands on systems already operating under constraint. Then there is the balance between alertness and fatigue. The brain relies on a steady supply of oxygen and glucose. It also relies on rest. Sleep is not optional maintenance. It is essential for cognitive function, emotional regulation, and physical health. In unusual environments, sleep quality suffers. Noise, vibration, confined space, altered light exposure, and psychological tension all interfere with rest. Even if someone closes their eyes and remains still, true restorative sleep may not occur. Over time, sleep deprivation affects attention, reaction time, and judgment. In an environment where small mistakes can have serious consequences, this matters. The immune system is also sensitive to stress and environment. Stress hormones suppress certain immune responses. Disrupted sleep weakens immune function. Altered air quality and humidity can affect respiratory defenses. Over longer missions, these changes increase vulnerability to illness, even in environments designed to be clean and controlled. The digestive system, often overlooked, plays a role as well. Digestion depends on regular rhythms and blood flow patterns. Stress diverts blood away from the gut. Motion, even subtle vibration, can induce nausea. Appetite may decrease or become irregular. Nutrient absorption can be affected. While these issues may seem minor, they influence energy levels and overall resilience. All of these systems are interconnected. A change in one affects the others. Slightly elevated carbon dioxide levels can increase breathing effort and anxiety. Anxiety increases heart rate and stress hormone release. Stress hormones affect sleep and digestion. Poor sleep worsens cognitive function and emotional regulation. The result is a gradual narrowing of tolerance. This is what makes the internal balance so fragile in extreme environments. It does not collapse all at once, it drifts. Small deviations accumulate. Each by itself may be manageable. Together they erode the margin that keeps everything running smoothly. On the surface, the environment constantly helps restore balance. Fresh air dilutes carbon dioxide. Sunlight regulates circadian rhythms. Space allows movement and posture changes. Social interaction provides psychological grounding. Even simple things like walking, stretching, and changing rooms contribute to physiological regulation. In the Mariana Trench, none of this is available. Everything that maintains balance must be engineered, scheduled, and monitored. This includes air composition, temperature, humidity, lighting, activity, rest, and nutrition. The more time passes, the more opportunities there are for something to drift slightly out of range. Deep-sea missions are designed to minimize this drift by keeping duration short. The goal is not to test how long humans can endure imbalance, but to gather information before imbalance becomes significant. This is a practical decision, not a philosophical one. It is also important to recognize that individuals vary. Some people tolerate confinement and stress better than others. Some adapt more easily to altered sleep cycles. But no human is immune to the cumulative effects of an environment that continuously pushes against biological expectations. Contrast this with deep-sea organisms. Their internal balance is matched to their surroundings. Pressure inside and outside their cells is equal. Temperature is stable. Light is irrelevant. Their metabolism is slow and efficient. They are not constantly correcting for mismatch. They are in equilibrium. Humans are not. Every moment at extreme depth requires correction, active maintenance, attention, energy. That effort can be sustained for a time, but it cannot be sustained indefinitely without cost. This is why staying longer does not simply mean staying longer. It means accepting increasing risk of internal imbalance, risk of fatigue, risk of impaired judgment, risk of system failure, both mechanical and biological. And as that internal balance becomes harder to maintain, the environment begins to expose another vulnerability, one that is less about chemistry and physiology and more about structure. Because under extreme pressure, even the body's physical form, the way tissues and organs are arranged and supported, starts to encounter forces it was never meant to endure. The idea of the body being squeezed tends to conjure dramatic images. Bones snapping, organs bursting, everything collapsing inward in an instant. It's an understandable picture, shaped by movies and exaggerated stories about deep-sea pressure. But what actually happens when the body is exposed to extreme pressure, or even when it exists near it for extended periods, is quieter, more complex, and in many ways more unsettling. It is not about sudden destruction. It is about gradual interference with systems that depend on space, flexibility, and balance. The human body is not rigid. That flexibility is one of its strengths. Tissues stretch, compress, and shift constantly. Blood vessels expand and contract. Lungs inflate and deflate. The stomach and intestines move and change shape as they work. Under normal surface conditions, these changes happen within a comfortable range. Pressure from the outside world is stable and predictable, and the body's internal pressures are calibrated against it. Extreme pressure disrupts that calibration. When pressure increases uniformly around the body, solid and liquid components resist compression relatively well. Water, which makes up a large portion of our tissues, does not compress easily. Muscles, organs, and connective tissue do not suddenly flatten. But the body is not a sealed, homogeneous mass. It contains spaces, cavities, interfaces between tissues of different densities. It relies on subtle differences in pressure to keep things moving. The lungs are the most obvious vulnerability. They are filled with air, and air compresses readily. Under increasing pressure, air-filled spaces shrink. If the surrounding pressure rises faster than the air pressure inside the lungs can be increased to match it, the lungs collapse. This is why unprotected descent into deep water is immediately fatal. The lungs cannot maintain their structure against the force pressing inward. Even when air pressure is artificially maintained, as it is inside a submersible, the body is still affected indirectly. The surrounding environment exerts pressure on the vessel, and the vessel in turn transmits vibrations, temperature changes, and subtle stress to its occupants. These effects are not crushing, but they are not neutral either. Pressure also affects the ears and sinuses. These spaces are connected to the outside world through narrow passages that allow pressure equalization. At depth, managing this balance becomes critical. Any blockage, inflammation, or dysfunction can lead to pain, disorientation, or injury. In extreme cases, pressure differences can damage delicate structures in the inner ear, affecting balance and hearing. Balance is particularly sensitive. The vestibular system in the inner ear relies on fluid movement and gravity to provide information about orientation and motion. In confined environments with limited movement and altered sensory input, this system can become confused. Pressure itself does not directly damage it in a pressurized vessel, but the combination of confinement, vibration, and sensory deprivation can interfere with its normal function. Blood vessels, especially capillaries, also experience the effects of compression. Capillaries are tiny, thin-walled vessels that allow exchange between blood and tissues. They are designed to operate under specific pressure ranges. Changes in external pressure can alter how fluids move across capillary walls. This affects tissue hydration, nutrient delivery, and waste removal. Over time, even small disruptions to these processes contribute to fatigue and discomfort. Swelling in the extremities, changes in circulation efficiency, and altered tissue pressure are not immediately dangerous, but they signal that the body is working harder to maintain equilibrium. The brain is particularly sensitive to pressure-related changes. It is enclosed within the skull, surrounded by cerebrospinal fluid that cushions and protects it. This system is designed to absorb minor changes in pressure and movement. Under extreme or sustained conditions, however, even slight alterations in fluid dynamics can affect intracranial pressure. Inside a pressurized vessel, intracranial pressure remains within normal limits, but indirect effects still occur. Changes in blood flow, carbon dioxide levels, and stress hormones influence cerebral circulation. Headaches, pressure sensations, and mental fatigue are common complaints in confined high-stress environments. These symptoms may seem mild, but they affect concentration and decision-making. Muscles and connective tissues also respond to sustained compression and immobility. When the body remains in a fixed position for long periods, pressure builds at contact points. On land, people shift positions unconsciously to relieve this pressure. In a submersible, movement is limited. Over time, this leads to discomfort, stiffness, and reduced circulation in compressed areas. This is not unique to deep-sea environments. Similar issues occur during long flights or extended bed rest. The difference is that in the Mariana Trench, these effects occur alongside heightened stress and limited ability to intervene. Stretching, walking, or changing posture significantly may not be possible. Pressure also affects joints. Joints rely on synovial fluid for lubrication and shock absorption. Changes in pressure and temperature can alter the viscosity of this fluid. Combined with limited movement, joints may feel stiff or painful. Again, this is not catastrophic, but it contributes to cumulative strain. The digestive system experiences compression-related effects as well. The stomach and intestines are flexible and responsive to pressure changes. Altered pressure dynamics can influence how gases within the digestive tract behave, leading to bloating or discomfort. Stress further affects gut motility and secretion, compounding these sensations. At the cellular level, pressure influences membrane behavior. Cell membranes are dynamic structures composed of lipids and proteins. Their function depends on maintaining specific shapes and fluidity. Extreme pressure can alter membrane properties, affecting how receptors work and how signals are transmitted. While pressurized environments protect against direct external pressure, prolonged exposure to stress-related physiological changes can still influence cellular behavior. One of the less obvious effects of being squeezed by an extreme environment is how it changes breathing mechanics, even in a controlled atmosphere. When the body is under stress, breathing patterns shift. Shallow breathing becomes more common. Chest wall movement may be restricted by posture and confinement. This alters oxygen and carbon dioxide exchange, feeding back into blood chemistry and cerebral blood flow. These effects form a loop. Physical compression and confinement increase stress. Stress alters breathing and circulation. Altered breathing and circulation affect brain function. Reduced brain function impairs the ability to manage stress. Over time, this loop tightens. It is important to emphasize that none of this means the body immediately fails. Humans can tolerate a surprising amount of discomfort and physiological strain. The issue is not whether the body can endure being squeezed for a while, it is how long it can do so without errors accumulating. In environments with high margins for error, minor discomforts can be ignored. In the Mariana Trench, margins are narrow. The environment outside the vessel is unforgiving. The systems keeping occupants safe are complex and interdependent. Physical discomfort that distracts attention or slows reaction time becomes a safety concern. Deep-sea organisms experience pressure in an entirely different way. Their bodies are not resisting compression. They are balanced with it. They lack air-filled spaces. Their tissues are structured to function at ambient pressure. Their proteins and membranes are adapted to remain stable under compression. For them, pressure is not something acting on the body. It is the condition the body exists within. Humans cannot replicate this equilibrium. We must maintain an internal environment that resists the external one. This resistance is inherently stressful. It requires constant energy and attention, even when everything appears stable. The longer the body remains in this state, the more likely it is that small issues become noticeable. Numbness, headaches, muscle aches, reduced fine motor control, slight delays in thinking. None of these are dramatic. All of them matter. This is why deep-sea missions prioritize efficiency. Tasks are planned in advance. Time at depth is minimized. There is no benefit to lingering once objectives are met. Staying longer does not make the environment safer or more familiar. It increases exposure to stresses that cannot be eliminated, only managed. The sensation of being squeezed, then, is not a single event. It is a collection of subtle pressures acting on different systems at different rates. It is the body being asked to function while constantly compensating for an environment that presses inward, limits movement, and strips away familiar cues. Understanding this helps explain why humans cannot stay long in the Mariana Trench. Not because we would be crushed instantly, but because our bodies are not designed to operate for extended periods under conditions that require continuous correction and resistance. And as the body works harder to maintain its shape and function, another reality becomes clear. The only reason humans can reach these depths at all is because machines take on the pressure for us. Those machines, unlike living tissue, have limits of their own. And the difference between what machines can endure and what humans can endure shapes the boundary between visiting the deep and staying there. The only reason humans have ever laid eyes on the bottom of the Mariana Trench is because something else went there first. Not a person, but a machine. Every descent to those depths is a reminder of a simple truth that becomes clearer the deeper you go. Humans do not survive the trench by adapting themselves to it. They survive by refusing to meet it directly at all. Machines can visit because machines do not breathe, do not tire, do not panic, and do not depend on fragile internal balances to stay alive. They do not care about darkness. They do not feel cold. They do not experience stress in the biological sense. And perhaps most importantly, they can be designed to tolerate pressure in ways living tissue cannot. A deep-sea submersible is not an extension of the human body. It is a barrier between the human body and an environment that would otherwise make survival impossible. It creates an artificial pocket of surface conditions and carries that pocket downward through kilometers of water. Inside that pocket, air pressure remains stable. Oxygen remains breathable. Temperature is controlled. Outside, the ocean presses inward with unimaginable force. This separation is not optional. It is the entire premise of deep-sea exploration. When engineers design a vessel capable of reaching the Mariana Trench, the focus is not on comfort or convenience, it is on resistance. The hull must withstand constant uniform pressure without collapsing. This is why these vessels are often spherical, or nearly spherical. A sphere distributes force evenly. There are no corners to concentrate stress. Flat surfaces, which are easy to build and live in on land, become liabilities under extreme pressure. The materials used are chosen not just for strength, but for predictability. They must behave consistently under compression. They must deform slightly without cracking. They must not become brittle in cold temperatures. They must tolerate long periods under load without fatigue. Even then, safety margins are finite. Inside this hardened shell, humans exist as passengers, not participants in the environment outside. The vessel experiences the trench. The people inside experience the vessel. This distinction matters because it explains why humans cannot stay long even when machines can. A machine does not need to return to normal conditions immediately. It can remain at depth indefinitely if power and structural integrity allow. It does not suffer from disrupted sleep. It does not experience cognitive fatigue. It does not require fresh air in the way humans do. Remotely operated vehicles and autonomous underwater vehicles routinely spend long periods at depth. Some sit on the seafloor for months, collecting data, monitoring conditions, and transmitting information back to the surface. They are built to tolerate pressure, cold, and darkness as default states. Their systems are optimized for it. Humans are not. When a human enters a submersible, the machine must do more than resist pressure. It must also create a livable environment inside. This adds complexity. Oxygen must be supplied. Carbon dioxide must be removed. Temperature must be regulated. Humidity must be controlled. Lighting must be provided. Waste must be managed. All of this requires energy, space, and redundancy. Every one of these systems introduces potential failure points. The longer a mission lasts, the more opportunities there are for something to go wrong. Not necessarily catastrophically, but subtly. A sensor drifts out of calibration. A scrubber becomes less efficient. A battery depletes faster than expected. A component overheats. None of these problems are dramatic on their own. Together they limit duration. Machines can tolerate downtime. Humans cannot. A robot can power down non-essential systems to conserve energy. A human cannot stop breathing, stop producing carbon dioxide, or stop needing a stable temperature. Life support systems must operate continuously and reliably. That requirement alone places strict limits on how long a human can remain at depth. There is also the issue of redundancy. Every critical system must have backups. Backup oxygen, backup power, backup communication. Each backup adds weight and complexity. Weight limits how much a vessel can carry. Complexity increases the number of components that can fail. Designers must strike a balance between robustness and practicality. As missions extend in duration, this balance becomes hard to maintain. Carrying enough resources for a brief visit is feasible. Carrying enough for days or weeks multiplies the challenges. The vessel grows larger. The hull must be stronger. The descent and ascent take longer. Risk increases at every stage. Machines do not care how long they are alone. Humans do. Inside a deep-sea submersible, the environment is controlled, but it is not natural. The space is small. Movement is restricted. There is no privacy. Noise from equipment is constant. Vibrations travel through the hull. Over time, this affects concentration and comfort. Even highly trained individuals experience fatigue under these conditions. Attention wanes. Minor irritations become distractions. Decision-making slows. These effects are well documented in other confined environments, such as submarines, spacecraft, and polar research stations. The difference in the Mariana Trench is that the margin for error is extremely thin. If something goes wrong on land, help is nearby. If something goes wrong in orbit, there are protocols and rescue contingencies. In the trench, there is no rapid rescue. There is only the vessel, the people inside it, and the environment pressing inward from all sides. Machines can be abandoned, humans cannot. If an autonomous vehicle fails at depth, it becomes part of the seafloor. Data is lost, equipment is written off. This is unfortunate but acceptable in the context of exploration. If a human-carrying vessel fails, the consequences are immediate and irreversible. This reality shapes how conservative mission planning must be. Because of this, human dives to extreme depths are rare. They are not routine operations. Each one is treated as an exceptional event, planned meticulously, executed cautiously, and concluded as soon as objectives are met. There is no incentive to remain longer than necessary. There is no advantage in testing endurance when the environment offers no room for recovery. The machine, by contrast, can linger. It can wait. It can continue observing without concern for internal balance or psychological strain. It can tolerate silence and darkness indefinitely. This difference becomes especially clear when considering communication. Humans depend on communication not just for data transfer, but for reassurance, coordination, and support. In the deep ocean, communication is slow and limited. Acoustic signals take time to travel. Bandwidth is low. Conversations are delayed. Real-time interaction is impossible. For machines, this is irrelevant. They operate autonomously or follow pre-programmed instructions. They do not require conversation. Humans do. Even when focused on tasks, humans are aware of isolation. Over time, that awareness becomes a stressor. The psychological aspect of machine versus human endurance cannot be overstated. Humans evolved in social groups. Isolation is perceived as risk. Even when intellectually understood as safe, the emotional response persists. The trench offers no cues of safety. It offers no signs of life at human scale. It offers no sense of belonging. A machine does not need to feel that it belongs. It only needs to function. Another factor is adaptability. Machines can be built specifically for one environment. A deep-sea vehicle does not need to function anywhere else. It does not need to walk, run, see in daylight, or interact socially. Its entire design can be optimized for pressure, darkness, and cold. Humans carry evolutionary baggage. We cannot turn off systems we do not need. We cannot shed sensory expectations. We cannot slow our metabolism to deep sea levels. We cannot eliminate our reliance on oxygen-rich air. Every adaptation we bring is a workaround, not a transformation. This is why, even as technology improves, the fundamental relationship does not change. Machines will always be better suited to prolonged presence in the Mariana Trench than humans. Human presence will remain brief, purposeful, and heavily mediated. It is tempting to imagine a future where humans build permanent habitats on the ocean floor. Science fiction often explores this idea. But when examined closely, such habitats would face the same constraints as submersibles, magnified by time. Continuous life support, constant pressure resistance, limited evacuation options, cumulative stress on materials and people. The ocean does not become more forgiving simply because we stay longer. Pressure does not ease. Cold does not relent. Darkness does not adapt to us. The environment remains exactly what it is, indifferent to human presence. Machines thrive under indifference. Humans do not. This does not diminish the achievements of deep-sea exploration. On the contrary, it highlights them. Every successful human descent into the Mariana Trench represents a triumph of engineering over environment and discipline over impulse. It is not about conquering the ocean. It is about borrowing a small amount of time in a place that does not want us there. And that borrowed time is always limited. As we move forward, it becomes important to look at the few moments when humans have actually made that journey. The rare descents that prove it can be done, but also quietly reinforce why it cannot be done for long. Very few humans have ever been to the bottom of the Mariana Trench. Not a handful in the casual sense, but a literal handful. Fewer people have stood at the deepest point of the ocean than have walked on the surface of the moon. That fact alone tells you something important. This is not a place humans gradually became comfortable visiting. It is not a destination that opened up through repeated exposure and routine missions. Each descent has been an exception, treated as something singular, cautious, and deliberately limited. The first lesson from those who have gone down is that reaching the bottom is not the hard part in the way people often imagine. The technology exists. It has existed in some form for decades. The challenge is not curiosity or bravery. The challenge is everything that comes with being there, even briefly. The earliest descents were exercises in uncertainty. When the first crewed submersibles made the journey, engineers and scientists knew the theory. They understood pressure mathematically. They trusted the materials they had tested in laboratories, but theory and practice are not the same thing, especially when the environment is so far removed from anything that can be simulated fully on the surface. Those early crews described the descent as long, quiet, and strangely uneventful. Hours pass with little to see outside the viewport. Darkness arrives early and never lifts. Instruments become the primary connection to reality. Depth numbers climb steadily. Pressure gauges move into ranges that feel abstract even to trained minds. The surface becomes a concept rather than a place. One of the first lessons was how completely the environment strips away human reference points. There is no visual sense of speed or distance. The descent feels almost motionless. Without the readouts, you would have no idea how far you had gone or how much water now sat above you. This disconnect between experience and reality is subtle, but it matters. Humans rely on sensory feedback to assess risk. In the trench, that feedback is absent. When the bottom is finally reached, it does not announce itself dramatically. There is no grand reveal, no sweeping landscape. The lights illuminate a small patch of sediment, perhaps a few rocks, maybe a faint disturbance as the vehicle settles. The world beyond that narrow circle remains invisible. The immensity of the trench is understood intellectually, not emotionally. Those who have been there often remark on how ordinary it looks, at least at first glance. Flat, quiet, still. This ordinariness is deceptive. It hides the fact that every square centimetre outside the hull is under crushing pressure, that the environment is lethal without protection, that the margin for error is essentially zero. Another lesson is how quickly time becomes the dominant factor, not because of boredom, but because of limits, battery life, oxygen supply, carbon dioxide scrubbing capacity, thermal control. Every system has a finite operating window. The longer you remain, the more those windows close. Even in well-designed submersibles, crews report a constant awareness of duration. Not anxiety exactly, but attentiveness. You do not forget where you are. You do not forget that ascent will take hours. You do not forget that help is impossibly far away. This awareness shapes behaviour. Movements are deliberate. Conversations are focused. There is little wasted effort. The few who have gone down also describe how physically constrained the experience is. The vessels are small by necessity. There is no room to stretch out. Posture becomes fixed. Muscles tire from holding the same positions. Small discomforts accumulate. None of this is dramatic or heroic. It is mundane, persistent, and draining. This physical strain reinforces another lesson. The human body does not settle into the environment. It does not relax and adapt. It endures. There is a difference. Endurance implies effort. Adaptation implies equilibrium. In the trench, humans never reach equilibrium. The body is always compensating. Crews have noted subtle changes in perception and focus as time passes. Nothing severe enough to stop the mission, but enough to notice. Attention narrows, fatigue creeps in. Tasks take slightly more effort. This happens even on dives that last only a few hours at the bottom. It is not a failure of training. It is a predictable response to confinement, isolation, and stress. One of the most important lessons comes from what did not happen. Despite decades of technological progress, no one has stayed. No one has attempted to extend a visit simply to see if it could be done. The goal has always been observation, sampling, documentation, and return. The bottom of the trench has never been treated as a place to occupy. This is not because scientists lack curiosity. It is because the cost of staying longer is obvious to anyone who has been there. Risk increases without adding meaningful reward. The environment does not change. The data does not improve simply because a human is present for more hours. Machines can continue observing without fatigue. Humans cannot. Another lesson is how dependent humans are on redundancy. Every successful descent relied on multiple layers of backup. Redundant power systems, redundant life support, redundant communication. Even with these precautions, unexpected issues have occurred. Equipment failures, sensor malfunctions, structural noises that required careful evaluation. None of these incidents resulted in disaster, but they reinforced a central truth. The trench is not forgiving. There is no room to troubleshoot slowly. Problems must be anticipated and prevented, not solved after they arise. This mindset naturally limits mission duration. Those who have gone down also speak about the psychological effect of returning. Ascending back to the surface brings gradual reintroduction of light, colour, and sensory richness. Communication becomes clearer. The world expands again. Many describe a sense of relief that is not dramatic but deeply felt. This relief is telling. It suggests that even when everything goes according to plan, the experience carries a weight. Not fear, necessarily, but tension. The kind that comes from sustained vigilance. From knowing that survival depends on systems behaving exactly as intended. Another lesson is that human presence adds complexity to exploration. Life support, safety considerations, and psychological factors all compete with scientific objectives. Machines simplify this equation. They can be deployed more often, they can stay longer, they can take risks humans cannot. As a result, modern exploration increasingly relies on uncrewed vehicles. Human dives are now rare, symbolic, and highly focused. They serve to demonstrate capability, validate technology, and provide a human perspective. They are not the primary method of study. This shift reflects an understanding earned through experience. Humans are valuable observers, but they are not well suited to prolonged exposure at extreme depth. The trench does not become more understandable because we sit in it longer. It becomes understandable through data, repetition, and patience, qualities machines excel at. The few who have gone down have not returned with tales of conquering the deep. They have returned with respect for it. A recognition that it is a place where human presence is always temporary, always borrowed. They have also returned with a clearer sense of scale. Not just physical scale, but biological scale. The realization that life on Earth occupies many niches and that humans are specialized for only a narrow slice of them. The trench exists outside that slice. Perhaps the most important lesson is that there is no shame in limitation. The goal of exploration is not to prove endurance at any cost. It is to learn. And learning sometimes means recognizing when observation is better than occupation. The Mariana Trench does not invite us to stay. It allows us to look, briefly, carefully, and then it reminds us quietly to leave. And as we continue, that contrast between brief human visits and the permanent residence of the trench becomes impossible to ignore. Because while humans struggle to remain for hours, other forms of life spend their entire existence there, perfectly adapted to conditions we can only tolerate through layers of metal and machinery. While humans descend into the Mariana Trench as visitors, every movement planned and every minute counted, there are creatures for whom this place is not extreme at all. It is home, not a temporary stop, not an alien landscape to be endured, but the only environment they have ever known. They are born there, live there, feed there, and die there, under pressures that would destroy a human body instantly, in darkness that would disorient us beyond usefulness, and in cold that never lifts. The existence of life at such depths was once considered unlikely, even impossible. For a long time, scientists assumed that beyond a certain pressure, biological systems could not function. Proteins would lose their shape, cell membranes would fail, chemical reactions would slow to nothing. Life, it was thought, required gentler conditions. The trench proved that assumption wrong. Life at extreme depth does not resemble life at the surface, not in structure, not in behaviour, and not in pace. These organisms are not simply surface creatures pushed deeper over time, they are fundamentally different in how they are built and how they function. One of the most striking differences is what they lack. Most deep trench animals have no gas-filled spaces at all, no lungs, no swim bladders, no cavities that would collapse under pressure. Their bodies are composed almost entirely of soft tissues and fluids that are already in equilibrium with the surrounding water. Pressure outside their bodies is matched by pressure inside. There is no squeezing, no resistance, no need for reinforcement. The environment presses in, and the body simply exists within it. This is the opposite of how humans survive at depth. We survive by creating a rigid boundary and holding pressure back. Trench creatures survive by never holding it back in the first place. Their bones, if they have any, are often minimal or flexible. Many species are gelatinous, translucent, or soft-bodied. To a surface observer they might appear fragile, but in their environment they are perfectly suited. Rigidity is a liability under pressure. Flexibility is strength. Their proteins are another key adaptation. Under high pressure, the three-dimensional shape of proteins can change, interfering with their function. Trench-dwelling organisms produce pressure-adapted proteins that remain stable and functional under compression. Their cell membranes are composed of lipids that maintain proper fluidity despite cold temperatures and immense pressure. These are not small adjustments. They are fundamental biochemical differences. Metabolism in the trench is slow. Food is scarce. There is no sunlight to power photosynthesis. Most energy enters the deep ocean as falling debris from the surface, bits of dead plankton, waste and organic matter drifting down through kilometres of water. This slow rain of nutrients is known as marine snow, and it is often the primary food source for deep-sea life. Because food arrives unpredictably and in small amounts, trench creatures are efficient. They waste little energy. Many move slowly. Some remain almost motionless for long periods. Growth is gradual. Lifespans can be long compared to similar-sized animals at the surface. Predation still exists, but it follows different rules. There is no chasing prey over long distances. Energy expenditure must be minimized. Some creatures rely on ambush tactics, others scavenge. Some use bioluminescence to lure prey close enough to capture with minimal effort. Bioluminescence is one of the most remarkable features of deep-sea life. In the absence of sunlight, many organisms produce their own light through chemical reactions. This light is not decorative. It serves specific purposes. It can attract prey, confuse predators, or help individuals recognize members of their own species. For humans observing from a submersible, these flashes of light can feel eerie and unpredictable. For the organisms producing them, they are tools as ordinary as eyesight is to us. Sensory systems in trench creatures are adapted to darkness. Vision, when present, is often tuned to detect faint light, or bioluminescent flashes rather than detailed images. Some species rely more heavily on chemical sensing, detecting changes in the water that signal food, danger, or potential mates. Others are sensitive to vibrations and pressure waves, allowing them to perceive movement without seeing it. Reproduction in the trench is also shaped by scarcity and distance. Finding a mate in a vast, dark environment is not easy. Some species release eggs and sperm into the water, relying on chance encounters. Others have evolved strategies to ensure reproduction when opportunities arise. In some cases, males are tiny compared to females and live attached to them, providing genetic material when needed. These strategies may seem strange from a human perspective, but they make sense in an environment where encounters are rare and energy must be conserved. Perhaps the most humbling aspect of trench life is how stable it is. While the surface world experiences constant change, seasons, storms, temperature swings, and ecological disruptions, the trench remains relatively constant. Cold, dark, high pressure. These conditions have persisted for millions of years. Life there has had time to adapt deeply and thoroughly. This stability stands in sharp contrast to the human experience at depth. For us, the trench is unstable, hostile, and stressful. For its inhabitants, it is predictable. Predictability allows specialization. Specialization allows survival. This difference highlights a key reason humans cannot stay long in the Mariana Trench. We are not just unsuited to the environment physically, we are unsuited to it biologically and evolutionarily. Our bodies are not optimized for pressure equilibrium. Our metabolism is too fast. Our sensory systems demand information the trench does not provide. Even with technology, we do not truly enter the trench ecosystem. We remain sealed off from it, observing through windows and cameras protected by metal and machinery. The trench does not accept us as participants. It tolerates us briefly as observers. The creatures that live there do not need protection. They do not experience the environment as dangerous. They do not fight pressure, cold, or darkness. They are expressions of those conditions shaped by them over countless generations. There is another lesson here, one that goes beyond biology. The trench reminds us that life does not require comfort, at least not by human standards. It requires compatibility. Where compatibility exists, life thrives, even under conditions we consider extreme. Where it does not, no amount of willpower can substitute. Humans often imagine exploration as a process of expansion, of pushing boundaries outward and claiming new spaces. The trench suggests a different perspective. Some spaces are not meant to be occupied by us. They are meant to be studied, respected, and left largely undisturbed. This does not diminish human curiosity. It refines it. It encourages us to ask not just where we can go, but where we belong. As we observe trench creatures through cameras and sensors, we are reminded that Earth is not a single environment scaled up or down. It is a mosaic of worlds, each with its own rules. The surface is ours, the trench is not. And as we continue this exploration, that realization leads naturally to another question. If humans are so poorly suited to this environment, why did evolution take us in such a different direction? Why did our path lead upward and outward, rather than downward into the depths where pressure reigns and light never arrives? Humans did not fail to become creatures of the deep by accident. There was no missed evolutionary opportunity, no wrong turn that kept our ancestors from adapting to life under crushing pressure and permanent darkness. Evolution did not overlook the Mariana Trench and decide to try again later. It followed a path shaped by constraints, trade-offs, and the environments that rewarded certain traits over others. The result is a species exquisitely tuned to a narrow slice of Earth and fundamentally mismatched with places like the deepest ocean. Evolution does not aim for versatility in the abstract. It does not design organisms to survive everywhere. It responds to local conditions, reinforcing traits that increase reproductive success in a given environment and discarding those that do not. Over millions of years, this process produces specialization, not general-purpose resilience. Humans are no exception. Our evolutionary story begins in shallow water, then moves on to land. The earliest vertebrates that eventually led to mammals emerged in coastal environments, where pressure was low, light was available, and temperature varied within manageable bounds. As life transitioned onto land, new challenges arose: gravity without buoyant support, desiccation, temperature swings, and the need to breathe air rather than extract oxygen from water. Adaptations that solved these problems were rewarded, others were not. Once mammals became established on land, a new set of constraints locked in. Lungs replaced gills. Skeletons became load-bearing structures designed to resist gravity, not uniform compression. Blood circulation adapted to vertical pressure differences caused by standing upright. Vision evolved to work in air and light. Hearing adapted to vibrations through gas rather than water. These changes were not superficial. They reshaped anatomy, physiology, and development at every level. At the same time, mammals developed high metabolic rates. Warm-bloodedness allowed for sustained activity, endurance, and complex behavior. It also required a constant supply of oxygen and food. This strategy works extremely well in environments where energy is relatively abundant and conditions change frequently. It does not work well in environments where energy is scarce and conditions are stable but extreme. The deep ocean is such an environment. Down there, food arrives slowly and unpredictably. There is no sunlight to power photosynthesis. Metabolism must be efficient. Growth must be slow. Wasted energy is a liability. Evolution in that environment favors organisms that can survive on minimal input, tolerate constant pressure, and function without light. That path leads away from large brains, fast movement, and complex social behavior. Human evolution took the opposite route. Our ancestors benefited from mobility, problem-solving, and social cooperation. These traits required large, energy-hungry brains that depend on steady oxygen delivery and precise chemical balance, brains that generate heat and require cooling, brains that are sensitive to pressure, temperature, and sensory input. Once evolution committed to this path, retreating from it was no longer an option. Evolution is not a menu. You cannot simply swap one set of traits for another without consequences. A human adapted to deep-sea pressure would not be human in any recognizable sense. Lungs would have to disappear or be replaced. Bones would need to soften or become irrelevant. Metabolism would need to slow dramatically. Sensory systems would need to change. Reproduction strategies would need to adapt to isolation and scarcity. Social structures would become unnecessary or impossible. At that point, you are no longer describing a human ancestor that adapted to the trench. You are describing a completely different lineage. Another reason evolution did not push us downward is opportunity. For a trait to evolve, it must be useful where the organism already lives. There was no selective advantage for early humans to tolerate extreme pressure because early humans never encountered it. Evolution does not prepare organisms for environments they will never experience. It responds to present challenges, not hypothetical future ones. Surface environments offered abundant opportunities. Food sources diversified. Tools could be made. Fire could be controlled. Language could develop. Social learning accelerated adaptation faster than genetic change ever could. These advantages compounded over time, reinforcing a surface-oriented existence. Meanwhile, the deep ocean remained largely inaccessible. There was no path for gradual adaptation downward. Pressure increases rapidly with depth. There is no shallow stepping stone environment where mammals could slowly evolve tolerance. You cannot ease into 11,000 meters of water over evolutionary time unless each intermediate depth offers survivable conditions and selective benefit. For air-breathing, warm-blooded animals, it does not. Some mammals did return to the ocean: whales, dolphins, seals. This is often cited as evidence that humans might have done the same. But even these animals did not evolve to live at extreme depths permanently. They are divers, not residents. They surface to breathe. Their bodies are adapted to tolerate pressure temporarily, not indefinitely. Even the deepest diving whales have limits far above the depths of the Mariana Trench. Those limits are telling. They show how far mammalian physiology can be pushed and where it breaks down. Despite millions of years of aquatic adaptation, even whales cannot stay at extreme depths for long. They descend, perform a task, and return. The pattern mirrors human submersible dives: descend, observe, return. Different methods, same constraint. Evolution also shaped our psychology in ways that conflict with deep environments. Humans are exploratory, but we're also deeply reliant on social contact, sensory richness, and environmental feedback. We evolved in landscapes where movement revealed new information, where sight guided action, and where sound carried meaning. The trench offers none of this. In evolutionary terms, environments that provide little feedback and few opportunities for learning do not reward intelligence in the way surface environments do. There's little advantage to curiosity when the environment rarely changes and resources are scarce. Intelligence is expensive. It requires energy. Evolution favours it where it pays off. The trench does not pay off. This helps explain why humans experience discomfort, stress, and fatigue in environments like the deep ocean, even when physically protected. Our nervous systems are not merely reacting to danger, they are reacting to mismatch. Signals the brain expects to receive are missing. The environment does not respond to attention or action in familiar ways. Over time, this produces strain. Evolution built us to respond to variation, to notice change, to adapt behavior quickly. In the trench, variation is minimal, change is slow. The environment does not reward quick thinking or movement. This creates a sense of uselessness that the brain interprets as stress. Another factor is time. Human life history is shaped around relatively short lifespans, extended childhoods, and long periods of social learning. Deep-sea organisms often have long lifespans, slow reproduction, and minimal parental investment. These strategies are incompatible. A human population could not survive in the trench long enough to adapt culturally, let alone genetically. Even if technology allowed long-term habitation, evolution would not follow quickly enough to make it sustainable. Humans would rely indefinitely on artificial systems. Any failure would be catastrophic. There would be no natural buffer. Evolution favours robustness through integration with environment, not separation from it. This is the core reason humans cannot stay long in the Mariana Trench. Not because we are weak, but because we are optimised for something else entirely. Our strength lies in adaptability within a certain range, not in universal tolerance. The surface of Earth, with its moderate pressures, variable climates, abundant light, and diverse ecosystems, is where our traits shine. It is where intelligence, cooperation, and endurance offer real advantages. The trench is a different world, governed by different rules, rewarding different solutions. Understanding this is not a limitation of imagination, it is a clarification of identity. We are not meant to live everywhere, no species is, and as this realization settles in, it leads naturally to another question. If humans are so deeply mismatched with the trench, what actually happens when we push past our comfort zone and remain there longer than intended? At what point does endurance become danger? And how does the body signal that it has reached its limits? Isolation is often imagined as silence and solitude, a lack of company, an absence of conversation. But in extreme environments, isolation is something much more specific. It is the separation not only from other people, but from the familiar signals that tell the mind it is safe, oriented, and connected to the world it understands. In the Mariana Trench, isolation is not just physical distance from the surface. It is sensory, temporal, and psychological distance layered on top of one another until the mind is forced to operate without many of the anchors it normally relies on. Humans are social creatures in ways that go deeper than preference or culture. Our brains evolved to function in groups, surrounded by cues from other people and from shared environments. Facial expressions, body language, tone of voice, background noise, movement, and even casual proximity all contribute to a sense of normalcy. These signals constantly reassure the brain that it is part of a larger system, that help exists, that danger can be detected and responded to collectively. In a deep-sea submersible at the bottom of the Mariana Trench, almost all of these signals disappear. The crew is small, often only 1 or 2 people. Conversation is limited, not by lack of interest, but by focus and fatigue. There is no ambient human presence beyond those few individuals, no distant voices, no sense of a larger group nearby. Communication with the surface exists, but it is delayed, narrow and impersonal. Messages travel slowly through water as acoustic signals. Real-time dialogue is impossible. The knowledge that others are technically reachable does not translate into a feeling of connection. This separation alters how the mind processes stress. Under normal circumstances, humans distribute cognitive and emotional load across social networks. We share concern, seek reassurance, and subconsciously regulate one another's emotional states. In isolation, all of that regulation must happen internally. The brain becomes both the source of stress and the sole manager of it. This is exhausting. In the trench, the environment provides no relief. There is no change of scenery, no sensory novelty that feels grounding. The darkness outside the viewport is absolute. The space inside the vessel is fixed and unchanging. Over time, the mind begins to recycle the same thoughts, the same observations, the same concerns. Without new input, attention turns inward. Inward focus is not always harmful, but in high-risk environments it can amplify awareness of vulnerability. Every sound becomes noticeable. Every vibration invites interpretation. The mind starts to scan for meaning in neutral stimuli. This is not paranoia. It is an adaptive response to uncertainty. The brain evolved to detect threats early, especially when escape is limited. Inside a submersible, there is nowhere to go. No option to leave the situation. This lack of agency is psychologically significant. Humans tolerate stress better when they feel they have choices. Even if those choices are not exercised, their existence matters. In the trench, choices narrow. You're there until ascent begins. The schedule is fixed. The environment cannot be negotiated with. This creates a background tension that persists even when everything is functioning correctly. Time perception changes under these conditions. Without external cues, the brain loses its usual rhythm. Minutes may feel longer or shorter unpredictably. Attention may drift, then snap back sharply. Fatigue and alertness fluctuate in uneven patterns. This makes sustained focus harder to maintain. Sleep, if it occurs at all, is often shallow. The mind remains partially alert, attuned to sounds and sensations that might indicate a problem. This hypervigilance is adaptive in the short term but draining over time. Even a single night of poor sleep can impair judgment. Extended periods without true rest compound the effect. Isolation also affects emotional regulation. Small frustrations feel larger. Minor discomforts become more noticeable. Patience thins. This does not necessarily lead to panic or dramatic reactions. More often, it results in subtle changes, irritability, withdrawal, reduced communication. In a confined environment, these shifts matter. Cognitive performance is another concern. Studies from other isolated environments, submarines, polar stations, space missions, show consistent patterns. Attention narrows. Multitasking becomes more difficult. Reaction times slow slightly. Problem solving becomes more rigid. Creativity decreases. The brain prioritizes immediate concrete tasks over abstract thinking. In the Mariana Trench, this narrowing of cognition is not catastrophic, but it is limiting. Tasks must be performed precisely, instruments must be monitored carefully, decisions must be deliberate. Any reduction in cognitive flexibility increases risk. The mind also reacts to scale in unusual ways. Intellectually, occupants know where they are. They know the depth, the pressure, the distance from the surface. But emotionally, these facts are hard to integrate. The environment outside is too vast, too invisible, too absolute. The brain struggles to map itself into a space it cannot perceive. This can lead to a sense of unreality, a feeling that the situation is abstract or detached from normal life. Psychologists sometimes refer to this as derealization. It is not a breakdown or a loss of rationality. It is the mind's attempt to cope with an environment that does not fit its usual models. For short periods, this distancing can be protective. It allows focus without emotional overload. Over longer periods, it can become disorienting. The boundary between task-focused attention and emotional engagement blurs. Another aspect of isolation is responsibility. In extreme environments, the number of people involved is small, and roles are clearly defined. Each person's actions matter disproportionately. There is little redundancy in human roles, even if systems are redundant. This heightens pressure. The awareness that a mistake could have serious consequences, not just for oneself but for others, weighs heavily. This is not fear in the dramatic sense. It is sustained accountability, the kind that requires constant self-monitoring. Humans can maintain this level of responsibility for limited periods. Over time, it contributes to mental fatigue. Contrast this with environments where isolation is partial or temporary. A lone hiker can turn back. An astronaut has a team in constant communication. A submarine crew has dozens of people sharing the load. In the trench, isolation is both physical and social. There is no broader human presence to diffuse responsibility. This is why human dives are short, not because panic sets in, but because sustained isolation erodes performance predictably and measurably. The mind does not fail dramatically. It becomes less sharp, less flexible, less resilient. Machines do not experience this erosion. They do not care about isolation. They do not interpret silence as threat. They do not require social context to function. This is another reason they can remain where humans cannot. Deep-sea organisms also do not experience isolation as humans do. They did not evolve to expect social networks or environmental variation. Their nervous systems are simpler. Their behaviours are limited to what their environment supports. There is no mismatch between expectation and reality. For humans, isolation in the trench is not just being alone. It is being alone in a place that offers no reassurance, no familiarity, no sense of belonging. The mind works constantly to bridge that gap, and that work consumes energy. The longer a human remains under these conditions, the more the energy is depleted. Fatigue increases. Vigilance becomes harder to sustain. The risk of error grows, not because of fear, but because of cognitive load. This is why endurance alone is not the goal. It is not about proving that humans can tolerate isolation. It is about recognizing that tolerance has limits, and that those limits are shaped by how the human mind evolved. As isolation deepens and time stretches without familiar anchors, the question is no longer whether a human can remain in the Mariana Trench for longer, but whether doing so adds anything of value. At some point, staying longer does not increase understanding, it increases risk. And that brings us to the final practical boundary, not imposed by curiosity or courage, but by the simple arithmetic of safety. How long is too long, and who decides where that line should be drawn? There is no single number that answers the question of how long is too long at the bottom of the Mariana Trench. No stopwatch clicks over from safe to dangerous in an obvious way. Instead, that boundary exists as a shifting balance between systems, bodies, and probabilities. Time at extreme depth is not measured only in hours or minutes. It is measured in accumulated strain, shrinking margins, and how many things must continue working perfectly at once. At first glance, it might seem like a simple engineering problem. If a submersible has enough power, enough oxygen, and enough structural strength, why not stay longer? In theory, nothing dramatic changes after the first hour on the seafloor. Pressure remains constant, temperature remains constant, darkness remains constant. The environment is stable in a way few places on Earth are, but that stability is deceptive. The longer a human remains at the bottom, the more every system involved becomes part of a chain where failure does not need to be dramatic to be decisive. Life support does not need to stop entirely to become dangerous. A small reduction in efficiency, a gradual build-up of carbon dioxide, a slight temperature drift, or a minor sensor error can compound over time. Consider air management. Oxygen consumption is continuous. Carbon dioxide production is unavoidable. Scrubbing systems are designed with capacity and redundancy, but their effectiveness depends on chemical reactions, airflow, and mechanical reliability. Over time, filters degrade, absorbent materials approach saturation, fans and pumps experience wear. None of this happens suddenly, but it all moves in one direction. The same is true of power. Batteries discharge, fuel cells deplete. Power management systems balance competing demands: lighting, propulsion, heating, communication, life support. As reserves decline, choices narrow. Non-essential systems may be shut down to preserve essentials. Comfort decreases, flexibility decreases. The margin for unexpected events shrinks. Structural integrity follows a similar pattern. The hull of a deep-sea submersible is designed to withstand enormous pressure, but materials under constant load behave differently over time. Microscopic deformations can accumulate, seals compress, interfaces between components shift. Engineers account for this, but time remains a factor. The longer the hull remains under maximum stress, the more exposure there is to rare but consequential failures. Then there is the human element, which does not behave like a machine and cannot be paused or reset. The human body does not deteriorate instantly at depth. It copes, it compensates. But compensation has a cost. Energy is diverted. Stress hormones remain elevated. Sleep is shallow or absent. Muscles remain tense. Attention stays focused for longer than is natural. In the first hour or two, this heightened state can feel manageable, even productive. Focus sharpens, awareness increases, but as time passes, the same state becomes fatiguing. Reaction times slow. Minor discomforts demand more attention. Decision-making becomes more conservative, or occasionally more rigid. These changes are subtle. They do not announce themselves clearly. A person does not suddenly feel incapable. They simply feel slightly less effective than they were before. In everyday life, this would not matter. In the Mariana Trench, it does. Time also affects coordination between people. In small crews, communication patterns matter. As fatigue sets in, fewer words are used. Assumptions increase. Clarifications decrease. This is not negligence. It is a natural response to cognitive load and limited energy. Mission planners understand this well. They do not ask how long a human can survive at depth. They ask how long a human can perform reliably at depth. Those are very different questions. Survival implies enduring conditions without dying. Performance implies thinking clearly, responding accurately, and managing complexity. The second threshold is reached much sooner than the first. Another factor is ascent. Time at the bottom cannot be considered in isolation from the time it takes to leave. Ascending from the Mariana Trench takes hours. During ascent, systems remain under stress, albeit changing stress. Power is still consumed. Life support is still required. Structural loads shift. If something has degraded during the stay, ascent does not make it better. This means that any decision to stay longer must include enough margin not just for the present moment, but for everything that comes after. There must be reserve capacity for the unexpected during ascent, when options are even more limited. There is also the question of rescue, or rather the lack of it. At the bottom of the trench, rescue is not an active option. There is no rapid response capability. There are no nearby vessels that can intervene quickly. Any problem must be solved with what is already on board. This reality pushes acceptable durations downward. The longer the stay, the higher the probability that something will go wrong. Even if that probability remains small, the consequences are severe enough that it must be minimized. From a scientific perspective, there is another consideration. What is gained by staying longer? In many cases, very little. The environment does not change on human timescales. Geological processes are slow. Biological activity is subtle. Once observations and samples are collected, additional hours do not necessarily add meaningful information. Machines can continue monitoring without fatigue. Long-term data collection is better suited to autonomous systems designed to remain in place for months or years. Human presence adds perspective and judgment, but it does not need to be prolonged to be valuable. This leads to a practical definition of too long. Too long is the point at which risk continues to increase while benefit does not. That point arrives sooner in the Mariana Trench than in almost any other environment humans explore. There is also a psychological boundary. Humans can tolerate isolation, confinement, and stress for limited periods before performance declines measurably. This is not a personal failing. It is a biological reality observed across many extreme environments. Studies from spaceflight, polar expeditions, and submarine deployments show consistent patterns. Short missions are manageable. Longer missions require extensive support, rotation, and recovery. Even then, fatigue accumulates. In the trench, support and rotation are impossible. Recovery cannot occur until return to the surface. This makes conservative time limits not just sensible but necessary. Those limits are set collaboratively by engineers, physiologists, psychologists, and mission planners. They are not arbitrary. They are based on testing, modelling, and experience. Each successful dive reinforces them rather than challenging them. The history of deep-sea exploration does not show a trend toward longer human stays. It shows a trend toward better machines and shorter, more efficient human visits. This is not a failure of ambition. It is an optimization. Too long is also influenced by uncertainty. No system is ever fully understood. There are always unknowns. Materials behave differently over long durations. Human responses vary. Rare events cannot be predicted precisely. Time increases exposure to all of these uncertainties. By limiting duration, missions reduce exposure. They trade depth and novelty for safety and reliability. It is tempting to frame this as caution holding exploration back, but the opposite is true. Caution is what makes exploration possible at all. Without strict limits, the risk would be unacceptable, and human dives would cease entirely. So how long is too long? It is the point where the environment stops being observed and starts being endured, where attention shifts from learning to maintaining, where the cost of staying outweighs the value of being there. In the Mariana Trench, that point arrives quickly. This does not mean humans will never push the boundary again. Technology may improve, materials may become stronger, life support may become more efficient, but the fundamental relationship will remain. Humans will visit, machines will stay. And as we approach the end of this exploration, that distinction brings us to a final reflection. Not about how deep we can go or how long we can remain, but about what it means to encounter places that resist us completely, and why recognizing that resistance may be just as important as overcoming it. There's a quiet idea that runs through human exploration, one that is rarely stated outright but often implied. If we can reach a place, then surely we can learn to stay there. If we can survive briefly, then permanence is only a matter of time, technology, and determination. This idea has shaped how we think about deserts, polar regions, space, and the depths of the ocean. It suggests that every boundary is temporary, every limit negotiable. The Mariana Trench challenges that idea without drama or resistance. It does not repel us violently. It does not forbid entry. It simply exists in a state that does not accommodate us, and it does so consistently, quietly, and without exception. Some places are not meant to be inhabited, not because they are hostile in an emotional sense, but because they are complete unto themselves. They do not require us. They do not adjust to our presence. They do not offer compromise. The trench is one of those places. To say that a place is meant only to be seen does not mean it is unimportant or inaccessible. It means that observation, not occupation, is the appropriate relationship. Seeing allows understanding without disruption. It allows learning without forcing the environment to conform to human needs. This distinction matters more than it first appears. Humans are remarkably good at reshaping environments to suit themselves. We build shelters, regulate temperature, redirect water, alter landscapes, and introduce artificial rhythms of light and activity. In many places this works because the environment already sits close to the range we evolved to tolerate. Small adjustments are enough to bridge the gap. The Mariana Trench does not sit close to that range. It exists far outside it, not just physically, but biologically and psychologically. Every moment a human spends there depends on an artificial bubble that must remain perfect. The environment does not support us even minimally. It does not meet us halfway. This makes staying there different in kind, not just in degree. When humans live in harsh environments on land, there is usually some form of interaction. The body adjusts slightly. Behavior changes. Culture adapts. Over time, routines form. The environment becomes difficult but familiar. In the trench, familiarity never arrives. The body never stops compensating. The mind never relaxes into the setting. The environment remains alien no matter how advanced the technology becomes. Seeing, by contrast, has a different character. Seeing is temporary by nature. It accepts limits. It values perspective over permanence. When we see the trench, through cameras, sensors, and brief human visits, we learn about it without insisting that it accommodate us. This approach has practical advantages. It reduces risk. It preserves the environment. It allows machines, which are better suited to such conditions, to do most of the work. It recognizes that presence is not the same as understanding. There is also a philosophical dimension to this idea. Human history often frames exploration as conquest, as bringing distant places into the sphere of human control. Mountains are climbed, oceans are crossed, space is entered. These achievements are celebrated not just for what they teach us, but for what they symbolize about human capability. The Mariana Trench resists that narrative gently but firmly. We can go there, we can see it, but we cannot claim it as a place to inhabit. Not comfortably, not safely, not without continuous effort that offers diminishing returns. This resistance does not diminish human achievement, it refines it. It reminds us that understanding does not always require ownership, that presence does not always require permanence, that some environments are valuable precisely because they exist beyond our everyday reach. There is a tendency to view limits as failures, as something to be overcome eventually. But limits can also be signals. They tell us where our strengths apply and where they do not. They help define what kind of creatures we are. Humans are creatures of the surface, of moderate pressure, of open air, of light and shadow, of social spaces and sensory richness. Our bodies, minds, and cultures all reflect this. When we step outside that context, we can do so briefly, carefully, and with assistance, but we do not belong there in the way we belong here. The trench, in this sense, is not a challenge issued to humanity. It is a reminder offered. It reminds us that Earth contains many worlds layered on top of one another, each with its own rules. The surface world happens to be ours. The deep ocean belongs to different forms of life, shaped by different constraints and possibilities. Neither is superior, they are simply different. Seeing the trench allows us to appreciate this diversity without trying to flatten it into something familiar. It allows us to witness life that operates under rules unlike our own. It expands our understanding of what life can be without requiring us to become part of it. There is also humility in this approach. Humility not as self-doubt, but as accuracy. An accurate understanding of where we fit in the larger system of the planet. Humans are capable of remarkable things, but we are not universally adaptable. We do not need to be. Our achievements arise from working within our strengths, not denying our limitations. The desire to stay, to push further, to remain longer, often comes from curiosity mixed with identity. If we can stay, then we belong. If we belong, then the place becomes part of our story in a deeper way. But belonging is not always reciprocal. The trench does not incorporate us into its rhythms. It does not offer feedback that rewards extended presence. It does not become safer or more intelligible the longer we remain. It simply remains what it is. Machines can stay because they do not seek belonging. They do not need meaning or comfort. They can exist purely as tools of observation. Humans cannot easily adopt that role. Our presence carries needs that the trench does not meet. This is why the future of deep exploration will continue to look the way it does now. Brief human visits for perspective and validation, long-term machine presence for data and monitoring, a clear division of roles based on suitability rather than ambition. There is wisdom in that division. It allows humans to engage with the deepest parts of the planet without pretending that all environments are equally livable. It allows us to learn without forcing permanence. It respects both the limits of our biology and the integrity of the environment. Some places teach us most clearly when we do not try to stay. The Mariana Trench teaches us about pressure, adaptation, and the range of life on Earth. It teaches us about the boundaries of human physiology and psychology. It teaches us about the difference between visiting and inhabiting. It also teaches us something quieter, something easy to miss. Not every unknown needs to become familiar. Not every frontier needs a settlement. Some frontiers are better understood as windows rather than doors. When we look into the trench, we are not seeing a place waiting for us. We are seeing a place that exists entirely on its own terms. That existence is not diminished by our inability to remain there. If anything, it is clarified by it. In a world where humans increasingly reshape environments to fit themselves, there is value in recognizing environments that resist reshaping. They serve as reference points. They remind us that the planet is not built solely around human convenience. The trench will remain dark, cold, and silent long after our technology changes. Long after individual missions are forgotten. It will continue to host life adapted to its conditions, indifferent to our presence. We will continue to visit it, briefly, carefully, and with respect. We will continue to look, measure, and learn. And then we will leave. Not because we failed to stay, but because staying was never the point. Some places are meant only to be seen.